It's a great pleasure to welcome the General Consul of Türkiye, Mr. Hüseyin Emrah Kurt. Mr. Kurt will give us a brief speech to officially open the seminar. Please join me and welcome Mr. Kurt.
Good afternoon. First of all, I would like to thank for inviting me to this event, which is taking place with the participation of distinguished scientists I learned that 24 countries are also joining us from all over the world. Unfortunately, on February 6th, we faced one of the most devastating earthquake disasters, not only in Turkey, but also in human history. The earthquake was effective in a very wide area covering 11 provinces of Turkey. That means millions of people. And more than 50,000 of our citizens, people lost their lives during the earthquake. That days I was in Ankara. I'm new in Vancouver. I just came 1.5 months ago. During the earthquake, I was in Ankara. We felt it even in my capital, in our capital. But because of my duty those days, I visited the earthquake region very often after the earthquake. And I have seen firsthand the destructiveness of the earthquake. Even in some cities, there is no building left that was not destroyed or damaged. Immediately after the earthquake, all state institutions in Turkey and civil society organizations stepped in and continued to search and rescue efforts, but it wasn't an easy task because the area was very wide and large. Meanwhile, we also made a call for international aid, and we were very happy to see that we received widespread support from many countries. Search and rescue teams of 11,000 people from 90 countries came to Turkey to support search and rescue efforts. They built tent cities, they built field hospitals, and those days it was very meaningful for the people of Turkey. Also, USAR teams from Burnaby municipality were in Turkey to support those activities. So at this point, I would like to emphasize our gratitude to both our Canadian friends and international community for the support they've shown us. Following the earthquake, now a huge reconstruction activity is going on in the area. New housing construction process continue in the places where ground survey has been conducted. The first houses were already delivered to earthquake victims. At the same time, scientists from Turkey and all over the world are working in the field. In their relevant research areas. I believe that these studies will make significant contribution for the preparations for possible future earthquakes in Turkey and elsewhere in the world. So it's vital to learn the necessary lessons from the earthquake. And we would like to take the necessary precautions for the future and build the new cities according to scientific facts. In this context, I believe today's seminar and similar events are very important and will be guiding for everyone for future work. So thank you again for inviting me here. I wish the seminar to be successful and produce a fruitful outcome. Thank you. Thank you very much.
Good afternoon. Welcome to the seminar related to the Turkey earthquake event happened in this February. My name is Tony Young. I'm one of the professors in the Department of Civil Engineering. It's truly my honor and pleasure to really host this event and having many of the people attending this session in person. And just to let you know that we have 800 people registered for the event from 24 countries. They're all observing us online. So you are live right now. Very good. All right, so I've been asked for a task to give a general introduction. I'll jump right into it. First of all, we'd like to dedicate this seminar to the life lost during the 2023 Turkey earthquake event, and also the effort that we are putting together to the future to mitigate any life loss in the future earthquake. First of all, let me introduce our team. The team consists of myself, Professor Carlos Ventura, Professor Alemdar Bayraktar, Professor Svetlana Brzev, Dr. Mehrtash Motamedi from UBC. We also have Bishnu Pandey from BCIT, Allison Chen from EGBC, Jeffrey Salmon from Structural Engineer Ausenco, and Keshab Sharma from BGC Engineering, Şerife from AEU in Turkey, Omar from SUR from Rome, Italy, and Vehicle from University of Belgrade. We'd like to take this acknowledgement to thank you for coming today. And this event will not be possible without the financial support from UBC Applied Science, and the staff member who's sitting at the back to ensure all the technical and non-technical portion are working well. EGBC, Structural Engineer Association BC Certification Program, and the Canadian Association of Earthquake Engineering, which provided support for some of our members to attend these sessions. And also many of our contacts that we met in Turkey to make all this event possible. You are here today probably asking two questions. Will this earthquake in Turkey affect my life? Okay. And what did the team going to Turkey and what do they learn from there? Will anything happen in Turkey happen to me here in Vancouver or whichever cities you are sitting right now? And the answer is yes. Okay, everything we learn are extremely relevant to all the people who are sitting here. If you live on this planet Earth, earthquake is not going away. And why are there earthquakes? Well, we have to go all the way back to 4.5 billion years ago when Earth was formed. How was Earth formed? When the meteorites are hitting each other and creating a lot of heat energy. And the space is very hot, very cold, and this heat energy are suddenly trapped inside the center of the Earth. If today you have a very good technology and cut the whole Earth open, you will see the center of Earth is very, very hot and the space is very cold. Physics are telling us those heat are constantly radiant out to the space. And in some location on Earth, there are cracks where the energy are easier to release. That's where we start seeing frequent earthquake event in those regions. Okay. Past earthquake have shown us literally in a few minutes, we can destroy a city we took a century to build. Okay, this is a real photo taken from the San Francisco earthquake, completely destroyed the golden city of the United States. Where we are here today in British Columbia, we are also in one of the most seismic active regions in the world. Underneath us, south of us, there will be California, United States. If you keep on going south, we have Mexico. If you keep on going south, countries in the mid-America, and then we have South America, Chile. If you go around the Earth, you will start seeing you have a lot of earthquake activity in New Zealand. And if you keep on going up, we're seeing lots of earthquake activity in Indonesia, Taiwan, Japan, and Alaska. This is what we know as a Pacific Ring of Fire, location, some of the most seismic active region in the world. And also a lot of area in the Europe and the Middle East region where we're seeing lots of red color. Today, I'm going to bring you to the event in February 2023 in Turkey. For those of you who are familiar with Turkey, beautiful country, lots of wonderful history and great food. The earthquake actually happened in the southern middle portion of Turkey, close to the city Gaziantep. This is about 850 kilometers away from Istanbul, probably from here to Banff, from Vancouver to Banff. So relatively close distance that you can easily drive to that location if you wanted to. Right around there, this is close to Gaziantep. In the morning of February 6, 4:17 a.m., a significant earthquake, magnitude 7.8 earthquake, hits the region. A big earthquake hits the region, bring destruction, a shaking to the region, and many buildings and life were lost during that particular event. Sadly, less than 9 hours away and 100 kilometers within the 100-kilometer range, another major earthquake, magnitude 7.5 earthquake happened. While people are still doing the rescue, another second major earthquake hits the region and completely caused more destruction and death to the region. And it doesn't stop. Literally within 2 weeks later, in February 20th, another major earthquake continued to hit the region. A magnitude 6.4 earthquake hit the region and causes devastation to the entire region caused by the earthquake. And the earthquake still doesn't stop. Over the period for the next 3 months, from February 20 to May 6, there are recorded over 35,000 earthquakes in those regions. Many of them, over 500 of them, are with magnitude 4 and 5 earthquake that could be felt by us and could cause some damage. This earthquake has resulted to significant damage to the structure and the environment. Now we can see surface ruptures all across this area. Resulted to 11 major city centers in the regions heavily affected by the earthquake. This representing over 160 municipalities and over 1,300 villages are all affected. This area affected are greater than 100,000 kilometers square, and over 14 million are affected by this earthquake. Half of the population in Canada are affected by an earthquake like this. Sadly, over 50,000, and including people in Syria, over 60,000 people have died from this earthquake. And over 2.5 million number of buildings were significantly affected by the earthquake. Not 25,000, 2.5 million buildings were affected by this earthquake. We're talking about big cities, cities even bigger than Vancouver. This is a photo of Hatay, a population of 1.6 million. You can see very vibrant, beautiful cities. And after the earthquake, total devastation. This is a video created by my team, recorded by myself when we visited the site. Entire town, fully populated, completely destroyed by this earthquake. This shows the magnitude of the earthquake shaking. Next video shows us that this is the video we took while we were in the bus. Complete destruction of a big city, 1.6 million, totally taken down by this earthquake. To the impact that we could feel the power of this mother nature. Same thing, Kahramanmaraş, another big city, 1.1 million, after the earthquake, completely destroyed. Adıyaman, which we also visited, population 632,000, barely damaged after an earthquake. Osmaniye, another close to 560,000 people town, barely affected by this earthquake. Overall, based on the data we collected in the report we generated, there are over 2.5 million buildings are affected by this earthquake, and it's categorized into new building, old buildings. Majority of these buildings in these 11 major city centers, more than half of them are relatively new building built from 2000 onwards. Majority of those buildings are reinforced concrete structures, and they are residential buildings. We look into the damage to the building, and the result shows over 500,000 buildings are completely damaged and need to be demolished. Close to 130,000 buildings are moderately damaged and over 1.27 million buildings are lightly damaged and affected by the earthquake, caused a direct financial loss of $66 billion directly only to the building sectors. In light of this, over 2.2 million people do not have a place to go home, and shelter must be provided. In addition to that, this region badly hit by the earthquake are very into agriculture and farming. Over 14,000 farms are damaged and causes a direct additional loss of $2.2 billion loss. Into the education systems. This is looking into the education system for kindergarten all the way to high school, thus not including University of Higher Education. Over in the region, 11,699 institutes in their region, representing about 21% of all educational institutes in Turkey. This institute owns 20,340 buildings. Based on the initial assessment, which they have not complete, 8,000 buildings has already been assessed. 2% of those buildings already shows complete collapse. 15% shows severe damage, 9% shows moderate damage, and the rest are light damage. The direct financial loss to the educational system, $2.11 billion US dollars. Healthcare system. Our colleagues in Turkey are well prepared for this earthquake. The hospitals are well equipped with advanced technology. Later, you will see base isolation technology, but they're still seeing damage to the traditional structure where they're heavily damaged, the structure and equipment. Direct financial losses to the healthcare system, 4.3 billion US dollars. Cultural heritage. These are artifacts, statues that take millions of years to start accumulating. This is something that we cannot replace. But looking into the financial losses, just to replace them without the value that we're losing, from the initial assessment, 25% of the assessment they are looking, the financial loss is already reaching close to 500 million US dollars. In general, the social and economical impact to these 11 major city centers in Turkey affected more than 14 million people. More than 15,000 people have lost their life. Over 115,000 are injured from this. There are more than 2 million people who are needing a place to stay, and we need to replace them, and causing a direct financial losses to the country of 103 billion US dollars, representing around 9% of GDP of Turkey in 2023. This afternoon, we'll be going through detailed technical sections, starting from my colleague, Professor Alemdar, talking about the seismic effect of the region, geotech effect of the region, with the collaboration with Keshab, Dr. Keshab Sharma. Afterwards, I'll be presenting about the building code in Turkey. We wanted to know what do they do differently or similar to the Canadian and other worlds. After that, we have a break. After that, our colleagues will be presenting the performance of the residential buildings in Turkey, the performance of the school buildings in Turkey, and the performance of the healthcare facility in Turkey. We're followed by another break. Then we will have what happened to our colleagues in Turkey. How do they prepare, respond, and recover from this earthquake? In my personal opinion, our colleagues in Turkey are well prepared. They see major earthquake every 15 to 20 years. And they know exactly what to do when the minute earthquake happens. These are the lessons we must learn and bring it home to Canada and around the world to be ready for this major and inevitable event. Afterwards, we'll have a panel discussion where panelists will be sitting up here and will welcome you to ask your questions. And then I'll give a general conclusion and show you some of the photos we took as a team, excursion team, when we visit Turkey. Some of the good and the bad.
Hello everyone, my name is Alemdar Bayraktar. I am a visiting professor in UBC. This presentation prepared by Professor Carlos Ventura, Dr. Keshab Sharma and me. The content of the presentation is global and local seismic hazard map of Turkey, active faults in Turkey, historical seismicity of Turkey, main and aftershocks of the February 2023 Kahramanmaraş earthquake, and ground motion characteristic of the Kahramanmaraş earthquake. Turkey is located in one of the most seismically active regions in the world. The first earthquake hazard map of Turkey was published in 1945. Then 63, 72, and 96 was updated, and the last updated version is published in 2018. The seismic parameters are defined depending on the geographical location in the latest seismic hazard map for the 4 seismic levels. These are DD1, DD2, DD3, and DD4 earthquake. DD3 and DD4 earthquake level for used service earthquake. DD1 and DD are used for the design for the structures. Turkey is located between the Eurasian plate in the north and African Arabian plates in the south. The Arabian plate is moving towards the northeast with respect to Anatolian plate at approximately 10 millimeters per year. 2 main major faults of Turkey are North Anatolian Fault and East Anatolian Fault. The 2020 earthquake, Kahramanmaraş earthquake, occurred on the East Anatolian Fault. North Anatolian Fault lies between Karlova and Istanbul. The fault mechanism of East Anatolian Fault zone, which is about 450 kilometers long, is northeast trending left lateral streak-slip fault system that lives between Karlova and Hatay. The most damaging previous earthquake in Turkey are Erzincan earthquake occurred in 1939 with magnitude of 7.8, and the other big one, 1999, Kizmit Kocaeli earthquake with magnitude 7.6. There were many people died during this earthquake. For the year 2000 to February 6, Kahramanmaraş earthquake, the following destructive earthquake occurred on the East Anatolian Fault, which are Bingöl, Karlova, Doğanyol, Kovancılar, Sivrice, and Karlova earthquake. The last destructive earthquake in the city of Kahramanmaraş and its surrounding occurred approximately 500 years ago. A destructive earthquake has been anticipated in this area for a long time. During the Kahramanmaraş earthquake, 3 main shocks occurred in the same area. The first one is occurred on February 6 at 4:17 a.m. with magnitude of 7.8 with depth of 7.6 kilometers in the Pazarcık town. 10 minutes after the first main shock, an aftershock with magnitude 6.6 and a depth of 6.2 occurred very close to first main shock at Nurdağ town. 9 hours later, with magnitude of 7.5 earthquake at Elbistan town occurred and with depth of 7.0 kilometers. And about 2 weeks later, on February 20, Yayladağ earthquake occurred on the Yayladağ town with magnitude of 7.4. This earthquake occurred on the same area as can be seen from the map, and there were a total of more than 33,000 aftershocks in the region between the February 6 and May 6. Aftershock had magnitude ranging from 0.2 to 6.6. About 8 had magnitudes between 5 and 7 magnitude. These earthquakes fault mechanism is shown on this slide. The first main shock occurred the 3 segments, and segment 1 is Narlı fault, and segment 2 is Gölbaşı and Erkenek fault, and segment 3 Amunos fault. In the 7.5 Elbistan earthquake, it has been evaluated that both Çardak and Doğan Şehir faults ruptured simultaneously. After both earthquake shocks, surface deformation ranging from centimeters to 4 meters have been detected by the AFAD. The first main shock affected 11 cities most of them are big cities, as can be seen from the first image, and about 14 million people affected during the first main shock. And the second main shock, 7.5, affected Kahramanmaraş, Malatya, and Adıyaman city, and the third one, Yayladağ earthquake with 6.4, is affected Hatay city. Due to the Kahramanmaraş earthquakes, a total of more than 50,000 people lost their lives and more than 115,000 people were injured. And according to damage assessment dated May 2 from the ministry, a number of collapse on urgently demolished building in the region reported as more than 58,000, and while the number of severely damaged buildings is more than 200,000. The strong ground motion of the February 2023 Kahramanmaraş earthquake recorded by Turkish Accelerometric Database and Analysis System, which is operated by AFAD using more than 800 strong motion stations. All the data related with these earthquakes can be downloaded from this website. The peak of horizontal and vertical acceleration values of Kahramanmaraş earthquake are larger than the highest horizontal and vertical ground acceleration values of before earthquakes. Recorded maximum peak ground accelerations for the 7.8 measured along from the epicenter to the Hatay station, and for the 7.5 earthquake measured near the Elbis town and Göksun town. During the first main shock, maximum peak ground acceleration occurred in Hatay city, 150 kilometers from the epicenter, and the measured peak ground acceleration is about 1.4 G. During the 7.5 earthquake, measured maximum ground acceleration is about 0.6 G. And the last one, during the 7.4 earthquake, peak ground acceleration recorded about 0.78 G. The time series, spectra, and areas intensity of the first main shock, peak ground acceleration, can be seen from the slide, can be seen here. The maximum spectral acceleration reached about 5G. And for the 7.45 earthquake, the time series and spectra and areas intensity is shown on the screen. It can be seen from the spectra, the affected period from the most affected area for the period is from 0 to the 2 seconds. These are time series of ground velocity recorded during the first main shock and second main shock. It can be seen from the time series of the peak ground velocities that there are pulse-like ground velocities during the Kahramanmaraş earthquake, especially the peak ground velocity during the Kahramanmaraş earthquakes is more than 180 centimeters per second. When we look at the spectra, some station spectra from the Kahramanmaraş earthquake, it can be seen from the spectra, some station, the recorded acceleration values in horizontal and vertical direction exceed the design DD1 and DD2 design earthquakes. This picture shows the most affected city during the Kahramanmaraş earthquake, which is Hatay city. The left one before the earthquake, the right one is after the earthquake. It can be seen almost most of the building in the Antakya city center collapsed or heavily damaged during these three main shocks and aftershocks. There is a video for the Kahramanmaraş earthquake. You can use a link for the watching, and we have some conclusions. It can be stated that in addition to design and construction faces mistakes, there are some reason to the seismic characteristic of the Kahramanmaraş earthquakes, which are high seismicity intensity, very large peak ground acceleration, peak ground velocity, peak ground displacement, and spectral values. and back-to-back effect of the earthquake scans and near-fault basin and soil amplification effect and shallow earthquake effects and the long duration of ground shaking and epicenter's proximity to the many city centers and proximity of several cities to the fault lines and very long ruptured fault system and different fault fragment and underestimating of the seismic demands during the process. Thank you very much for your consideration. After that, Dr. Sharma will continue.
But my responsibility is I'm going to present on geotechnical effect. Okay, so I mean, I think most of us know that like there were several geotechnical effects such as ground rupture, landslides, liquefaction, dam and embankment failure, foundation failure, ground amplification, local site effects. There are several geotechnical effects over there, but I'm going to talk about a very few geotechnical case studies. So like basically I'm going to talk surface ruptures, liquefaction and subsidence, performance of dam. So multiple surface ruptures were manifested along the fault line that cross the infrastructures and damage to the infrastructures. So out of many surface ruptures, I'm going to present one of the examples. So this surface ruptures, we visited Isla here, and it's next to the state hospital. So I'm going to present some of the photo here, and then we notice that the vertical displacement is about 1 meter. So you can see over here, and then we can see this several, because as I mentioned that this surface rupture crosses several infrastructures, so it damages several infrastructures. And then the longest surface rupture produced by the first earthquake, that magnitude 7.8 earthquake, it stretches 300 kilometers with displacement up to 7 meters northeast from the Mediterranean Sea. And then the second surface rupture by the second earthquake is about 125 kilometers long, displacement up to 5 meters, and all those crosses across the several infrastructures like pipelines, highway, even buildings, so many things. So second, what I'm going to talk is liquefactions and subsidence. So just I would like to introduce what is liquefaction basically. So in brief, the liquefaction is the process by which the soil below the water table temporarily lost its strength during earthquake and behave as a viscous liquid rather than the soil. That means it's lost its strength, bearing capacity lost, and then structure can fail. So this is the earthquake affected area with the surface ruptures and the fault zones. You can see that the red dot are the liquefied area. So the liquefied sites were along the fault lines at several locations, but this might be attributed to the river valley following the East Anatolian fault line, and the river deposits in saturated conditions are prevalent and vulnerable to the seismic liquefactions. And similarly, widespread liquefaction on wetland and along the coastal lines were observed. And then liquefaction induced damage to buildings, bridge foundations, lifelines, port facilities, and other civil engineering infrastructures throughout the region were reported. And then Golbasi, the city located on the northeast of this earthquake affected area. So Golbasi is one of the most affected cities we visited. It suffered from the significant number of geotechnical failure, especially liquefaction and ground subsidence. The city built up after 1950s on a wetland, and then the compressible wetland sediments, very young geology, young subsedimentary deposits up to 21 meters thick. And this is of course relatively young and loose sediments with high groundwater water table that makes this land highly vulnerable to the liquefactions. And then liquefaction-induced ground and building failures were widespread in several locations in this city. Yeah, so this is the geological map of the Golbasi city. I'm not going to explain in details, and this is the soil profiles, and this is the standard penetration test. Okay, so yeah, you can see that the water surface, groundwater is up, it's almost at the surface, and the soils is relatively loose to dense, and the standard penetration test number is it's like less than 10, which is considered as loose to very loose to loose soil, which is very favorable for liquefactions. And then these the points I mark are the damaged building due to liquefactions. So you can see that the buildings looks intact, but the foundations sink into the ground like by 40 centimeter in this case, but some of the buildings sink into the ground by more than 1 meter. And then you can see several other photos from the city. So buildings looks good. Structural component looks good, but the because of the liquefactions, building tilted, and then some of them are uniformly settled. And then liquefaction induced, of course, liquefaction induced bearing capacity failure were more common in 5 to 7 story building. Most of these buildings are 5 to 7 story buildings as compared to the 1 to 3 story residential buildings. So the structure designs ignoring the soil condition, unfortunately, remains vulnerable. Yes. And then these are the, I think these are the recreational area just next to the Golbasi Lake, and there are a significant number of extensive lateral spreading phenomena such as like multiple parallel large fractures were observed along the northern, eastern, and southern lakefront. In some places, large section of the land were totally submerged into the lake. So, and then so if we see the soil conditions, it seems the lake was filled by the loose to medium dense granular materials to make the recreational area. And similarly, we visited another city, this coastal city, Iskenderun. Iskenderun is a coastal city along the Mediterranean Sea, and this over here, and the young marine deposits and reclamation fields dominate the coastal plain. All these plains are very young, relatively young, and relatively soft. And then soil along the coastal area include loose to medium dense sand and silty sand. Even you go a little bit away from the coastal area, the soils are loose to medium dense and severely damaged due to widespread lateral spreading and the liquefaction along the coastal front, and significant ground application was reported. Yeah, you can see some examples of the failure due to liquefactions. And then even if you see the standard penetration test conducted on the coastal front, the standard penetration number is less than 10 even. And so that highlights the soil is relatively soft and highly vulnerable to the liquefactions or settlements or subsidence. So yeah, performance of the dams. So many dams affected by the earthquakes. So because of the because of soil liquefaction, fault rupture through the dams, seismic compression of the earth field, crest cracking, concrete spalling, or damage to the spills. So, but based on, though we didn't visit many dams, but based on the reports available, the most of the dams performed relatively well, especially hydropower dam performed relatively well during this earthquake. So, and then, but one of the examples, one of the dams we visited, this is Kartal Kaya Dam. So this is a clay core earth-filled dam constructed in like 1972, and it's the crest height of stream level is 56 meter, and it stores 1.45 million meter cube water. And the purpose of this dam is irrigation, fishing, and recreational activities. And then this dam is very close to the epicenter of the first event, magnitude 7.8, and then moderate damage with the crack widths varying between 15 to 35 centimeter was observed, but when we were there, the dam was already repaired. And then just I would like to link with the like, especially of course there were several geotechnical effects, but in my presentations I presented like more case studies of liquefaction case studies. So even in Canada, just I would like to link with Canada. So the several locations in Western Canada, including Vancouver, has all these parameters that trigger liquefactions, like shallow groundwater table because of the along the rivers, along the coastal area, and loose sandy soil and nearby falls, and the Cascadia subduction zone with capacity to produce large earthquakes. So all these parameters are favorable to have widespread liquefaction in Western Canada, especially in lower land and wetland. So conclusions, so fault rupture on multiple segments of the fault that cross and damage the infrastructure. So widespread liquefactions on wetland and along the coastal line, this is as expected. And then embankment dam exhibited varied performance based on these several factors, like the edge of the dam, the type of materials, the distance from the epicenter, and based on several factors. And then land reclamation using the liquefiable material is problematic. If we reclaim the land using the liquefiable material without any mitigations for liquefactions, it can be problematic. This is the examples or lesson learned from Iskenderun city. And seismic microzonation and land use planning are key factors. So yeah, and then key message is seismic microzonation and land use planning are key factors. So land reclamation using liquefiable material is problematic. We have to design this mitigation measure as well. And then geotechnical consideration is equally important as structure. So poor geotech and good structure, even it doesn't work. Poor geotech, poor structure, it doesn't work. Good geotech, poor structure, it doesn't work. If we have good geotech, good structure, it may work. Thank you, that's all.
In the next 20 minutes, I'm going to present to you about what we have learned from the Turkish code. I really have to give credit to my colleague, Professor Alemdar, Svetlana, Brzev, who have worked closely with me in really understand how the Turkish building code works. It's really exciting, actually. Now I can actually give a lecture about the Turkish building code. Well, first of all, Turkey is one of those countries well experienced by the earthquakes. Every 15 to 20 years, we see one major earthquake. So if you want to bet your research on earthquake engineering, Turkey is a good place to go. Okay. From the early 40s to early 2000, 1940 to 2000, there are so many big earthquakes. Over 100,000 deaths and over 200,000 injury, and over 750,000 buildings are destroyed before the 2023 February earthquake that we're talking about today. This earthquake has shaped the way the building code works in Turkey. To give you some high-level history, Republic of Turkey, established in the early 1920s. For the first 20 plus years, there's really no formal building code being prepared to guide how this was done. In the 1940s, the Turkish government started adopting the Italian building code and started using that towards the design. And shortly after that, we started seeing two major earthquakes happening after the building code is formally adopted. We've seen the 1943 Tosya earthquake and 1944 Garade earthquake, both magnitude 7.2. Shortly after that, the first national building code in Turkey was established in 1944. Okay, and after the code was put together, 5 years later, they started cleaning it up and polishing it up. So the second version of the Turkish building code was published in 1949. And then once again, 4 years later, Turkish code was updated. And now with a strong emphasis how to design structures in seismic hazard zone, which they call it specification for structure in disaster zones. So from 1953, Turkey have already paid emphasis how to design buildings in earthquake. 1962, the building code was once again cleaned up, and now they include revisions about reinforced concrete structure, how they should be used to design in Turkey. Okay, and 1966, the Vrato earthquake, and 1967, Adapazari earthquake happened, both with magnitude 7.1. Okay, and the code was once again updated in 1968, where the building code started with strong emphasis with different effects for the dynamic effect related to earthquake. And you can bet, rest assured, shortly after that, another major earthquake hits Turkey. 1971, Bingo earthquake, magnitude 6.8 hits Turkey. And 1975, Las Diyarbakir earthquake hits Turkey. And this is also the same year Turkish decided to update their building code, 1975. In 1992, we have heard about that in recent years. The Özkan earthquake, 6.8, barely damaged disaster. And then Turkish updated building code to the 1998 Turkish building code, which is considered to be the first modern building codes in Turkey, which directly dealing with advanced technology we're doing here, very similar to what we're doing here in Canada, including dynamic analysis, model superposition procedures as that. In 1999, the Kocaeli earthquake and Duce earthquake, both magnitude 7 and above. Significant earthquake caused a lot of casualty and losses. Turkish started updating the building code again in 2007. And then 2011, the Van earthquake, magnitude 7 earthquake hits. And very recently, the latest code in Turkey was last updated in 2018, which in my personal opinion to be really robust. Let me take you back to the history, what happened in 1944. This is the first official building code in Turkey. To really get it going in the earthquake design area, the researchers, the government start putting maps. This is the first seismic hazard map in Turkey. They break the country into 3 zones: the red zone, the yellow zone, and all the red zone. Okay, if you are in the red zone, you are in a highly seismic area, and the way to design for earthquake, well, the heavier the building, the more load you should be designed for. So if you're in red zone, you need to design additional 10% of your structure that's considered earthquake load, 10%. If you're in a yellow zone, we need you to design the buildings 5% of the building weight as your earthquake load. If you're in a white zone, congratulations. You don't have to worry about earthquake. This is simple and easy. Life move on without consideration of earthquake. They distributed the earthquake forces after they calculated uniformly over the height of the building. And they also indicated clearly where you can or cannot build buildings. Some of them are common sense, some of them are not. For example, you should not build a building in swamp. You should not be building a building in soft soil. You should not be building in a very steep slope. So they wrote it down those locations, and those are the locations that you should not build your building. In the 1944, the second building code, once it's cleaned it up, they started with a good backbone and they started improving it. One thing they were saying that maybe we need to seriously consider how we account for the weight of the building. The weight of the building are not just the dead load, which we see in the structure. There are a lot of life load, furnitures, people. This will be considered to be shaking and created load. So the Turkish building code started including that. How much of the life load, the chairs and table, should we account for? And the way they make decision is depending on the functionality of your building. If it's a residential housing, not a lot of people using it, we will count all the life load, and then we take 33%, 1/3 of it, and add it down to be what we consider as the earthquake forces. If you have bigger houses or high-rise building, high occupancy, they may not have high-rise building in 1949, but high occupancy buildings, then all the life load plus the dead load need to be accounted for when you study for earthquake effect. They once again cleaned up the 3 zones. The first time, if you're on zone 1, you take 10% of the weight of the building and you design for it. In the second revision, they say maybe that's a bit onerous, and now we have way more weight we accounted for. So if in red zone, we take 4 to 2% of the total weight, dead load plus life load. How much more? Y2, Y4, it depending on the height of the building. Once again, if you're in the Y zone, don't worry about the earthquake. 4 years later, the Turkish building code was cleaned up one more time, and then it remained fairly similar to the 1949 Turkish building code. 1962, the Turkish colleagues made a major revision to their building code. First of all, they reamped and re-show you the new seismic hazard map. This time, going from 3 zones to 4 zones. So some of the regions which is the gray area was Y, may not be Y anymore. And the calculation of the amount of earthquake forces you need to account for depending on few factors. One, it's either 10% or 6% of that way you calculated depending on the height of the building that you're dealing with. And they understand that changes. The other factors affecting how much earthquake forces you should account for depending on if you're designing this building with a concrete structure or steel structures. It will be also affected, like my colleague showing, depending on the ground condition, it will change as well. Okay. In the 1968, our colleague in Turkey made a major revision to that building code. Okay. Many significant changes to it. Well, first of all, they started looking into concrete, reinforced concrete, and start putting requirement how you start build those concrete buildings. They started using spectral shapes. They're starting to see what we're doing today. Okay, so this is 1968. They started using spectral shapes and dynamic effect to quantify how much are the real earthquake we should account for. And they also introducing importance factor, same thing we're doing today. In a regular building, the important factor will be 1, but in very important building, hospitals or fire department station, we need to make sure they are functional. So they increase the level of importance and they designed it with 50% more earthquake load, just to make sure they remain functional after the earthquake. The way they calculate the earthquake forces is still based on the zone, based on the soil condition, and based on the importance factors. But this time, they also include the influence of the structural period. So the higher the building, the longer the period, that will also affect how much you should be designing for the building. Also, they make changes to how we design for the building. Prior to 1968, you calculate the earthquake forces as a ratio of the dead load. Now, 1968, you calculate the earthquake forces to the building depending on what kind of soil is my structure, what kind of structure I'm using, what's the structure period I have, and then we assign to the building, but we don't assign uniformly. So story 2, story 3, story 4 are different. And how much different? They uses the weight of the floor and height of the floor, very similar to what we're doing here today in Canada. Okay. 1975, our Turkish colleague once again ramped up the earthquake code because they are seeing earthquake every 10, 15 years. Crazy, yeah? And they realizing the code need to be further improved. This time, they did the study and they reshaped the map, seismic hazard map for the country to be 5 zones. Zone 1 all the way to zone 5. The amount of earthquake forces they designed it for is once again depending on where you are. And still, in certain part of the country, which is marked as white color, zone 5, that means there's no earthquake. Well, most of the time that I visited places, there are always high seismic zones. So maybe next time you wanted to go there for fun, the white zone may be somewhere you can go and check it out. Yeah. Very good. And it also depends on the ductility factors. Back in 1975, we understand designing the structure elastically, it's not so economical. We have to ensure the concrete and the steel can absorb the earthquake energy, and then we can actually design for more efficiency. So they provide a ductility, a coefficient factor, depending on what kind of structural material you are using. Once again, they uses the importance factor, but this time they kept the same important factor, either 1 or 1.5 for the building usage. This time, they amp it up by providing the design response spectrum, which is period dependent and soil dependent. They also, And in 1998, this is considered the first, let me take it one step back. 1975 is one building code, and 1998, so a period of 23 years. So you can see the 1975 play a significant role to the number of buildings being built in those 20 years in Turkey. Many of the buildings was hit by the earthquake are designed either by the 1975 earthquake building code or 1998 building code. The 1998 building code is considered the first modern building code in Turkey. To ensure it's really state-of-the-art, our Turkish colleague further refined the seismic shaking intensity, much clean and lines where things are. And clearly in the Gaziantep area, we see heavy earthquake shaking. The amount of earthquake forces that we should account for is once again by zone. Remember, in the 1940 and 1944, the earthquake force was 10% or 5% of the building weight. In the 1998, they're realizing that we could no longer build building that way. They ramped it up to 40% of the building weight. Okay, so earthquake is no longer just another load. If you forgot to check, you're okay. This is so big that you cannot ignore it anymore. Okay, they fine-tune the importance factors. It's not just important or not important. They are somewhere in between. It's important, but not super important. So they started having important factor 1, 1.2, 1.4, 1.5. Very similar to the 2020 National Building Code in Canada, where we have been using it for the last 20 years. In terms of the intensity of earthquake shaking, they provide a design spectrum, which is soil dependent. If you're sitting in hard soil or soft soil, and then that will affect how much force you design for your building. In this building code, it also shows you different things you must consider. You need to start looking into irregularity, torsions, stiffness irregularity, strength irregularity, no different than what we're doing here today in Canada, where we have a whole series of irregularity that we try to tell engineers not to do. Also in that building code, it started using very close to what we do, a reduction factor, depending on the type of structural system we do. These are the reduction factor you can. And now you can start seeing that the code are getting very, very similar to our Canadian code. They started allowing use of model superposition, time history analysis, no different than what Canadians are doing here today. They're checking about the structural drift, same thing as what we're doing today. They can drift up to 0.3% under certain condition, 2% under different condition. And they also have minimum strength requirement for the material strength and also design shear. And there are many more detailing requirements which I'm going to push at the end. Afterwards, earthquake happened and they refined the code one more time. In 2007, our Turkish colleague made some minor changes to the 1998 building code because they did a significant change to that one. So, but there's still some new changes in the 2007 code. I listed down what's important. They add a chapter. The chapter is dedicated to assess and strengthen existing building. Canadian doesn't have such a code. We only have building code for new buildings. We don't have procedures for you to assess and strengthen existing buildings. 2, they started providing different level earthquake shaking, just like what we do in Canada, where they have small earthquake, medium earthquake, and high strength earthquake, high level shaking earthquake. They also have performance objective, what we're doing here in Canada. We want to make sure the building do not collapse, collapse prevention, immediate occupancy, and life safety performance objective. And they started allow engineers and researchers like yourself to assess the condition of building using pushover analysis. I can see many students sitting here in the room today. So the pushover analysis I teach you, you can use it. It's not fake, okay? 2018 is the latest and greatest building code right now in Turkey. And I really like it. It's really robust in my opinion. It has brand new seismic hazard map. And instead of putting into a zone, now they're doing what the Canadians doing as well. You're putting a street address, latitude or longitude, you know you're shaking. In the old days, it's by the zone. So if I'm in the left side of the zone, I have no earthquake. I'm on the right side of the zone. I have to design for earthquake of 5%, whatever percent. Now it's precise to your house, okay? Number 2, they started having very detailed description about how to design for reinforced concrete building, how to design for steel building, timber building, base isolated building are all in the code. The code are very clear indicating that they are not there to design for historical building, not there to design for lifeline, coastal structures, or port structures. This is also a code that they started dealing with vertical ground motion effect, which the Canadian has not included in our building code yet. Okay. And then this building code started dealing with multiple level shaking intensity. The Canadian has always been designing for 2 level shaking intensity. Earthquake comes every 2,475 years, and earthquake comes back. We have always been designing for the maximum credible earthquake. The Turkish are required to design for multiple level earthquake because they know the big one is going to hit them, but the small one is going to hit them sooner. So they need to make sure they are protected for the smaller one as well. They started to provide very clear classification about how you clarify the ground. Okay, and then they started providing tables for different soil conditions we can use. Yeah. So here, let me show you. And they introduced something fairly interesting. They started introduce something called building usage class. So whether you're a hospital, you're a school, what's the number, 0 or 1 or 5? I already passed the time. Very good. The class will be ending soon. Okay. So they have a building usage number. So if you're a hospital, you design for something, and then with the intensity and the building type, you will know what's the seismic design category, and with the seismic design category, with the higher the building, you know what's the high category that you require. And the building code give ways to tell you which way of the performance you must achieve. I'm going to show you just one last example since I don't have time. For example, if you have a new RC building that you need to design for, and you're designing for low-rise building, in that situation, if you are in design category 4, then the building code says that you need to design for the earthquake, which comes back every 475 years. And the performance objective you need to achieve is control the damage. And very similarly, if you have high-rise building at different category, they tell you the performance you wanted to achieve. Okay, I have one last slide that I would add, is that I'm very proud of my Turkish colleagues. They actually are not afraid of using novel technology, such as base isolation dampers, or hospitals in high seismic zone are required to be base isolated. And that's why we can see many of the performance of this hospital are performing very well.
Good afternoon. My name is Svetlana Brzev. I'm an adjunct professor at UBC Department of Civil Engineering, and I'm going to talk about performance of residential buildings. I would also like to add that all the technical glitches that you have seen today is only because today is Friday the 13th, and that is the reason it wouldn't happen otherwise. So, about residential buildings, I would like to thank, of course, all my colleagues whose beautiful photos I borrowed from and who contributed to the experience that I had in the field, and of course to all people in Turkey that we have met. So the outline of the presentation, I'm going to talk about construction practices for residential buildings, design codes, implications on what we have seen in terms of seismic performance, causes of damage and failure, typical examples, just a few to get a flavor of it, and just a few conclusions, even though there will be conclusions at the end. So residential buildings, in terms of construction practice, obviously reinforced concrete, as you have heard from the initial presentations, reinforced concrete construction is really governing a prevalent typology or construction technology for buildings in the affected area. And a major construction boom, according to what we have learned from the government officials and read about the affected area, major boom of construction practice in reinforced concrete construction took place in since 2000, and particularly in the area of high-rise buildings. So there are two common typologies. One is mid-rise buildings, the upper photograph, like up to 6-story high. They're multifamily residential buildings. And the others are high-rise buildings more than 10 stories high, 10 to 15 stories typically, even though they are taller buildings. So you can see those photographs. So in terms of the other buildings, obviously masonry is the other prevalent material in the field, but we have not seen too many masonry buildings during our visit. Our visit was focused on modern urban reinforced concrete buildings. And so this masonry construction is usually found in historic centers of like old center of the major city or rural areas, which we unfortunately haven't visited. And these are mostly unreinforced masonry buildings. They don't use reinforced masonry like we use here in Canada. They don't use confined masonry. So these are older unreinforced masonry buildings, very vulnerable, usually stone and adobe mud-based construction. So you can see here an example of a building that was in the city of Antakya. There are many beautiful old buildings. Some of them were converted into hotels, but they were severely damaged. This is an example of stone masonry with out-of-plane failure of the walls. So this is the photograph before and after. And we also visited some buildings, adobe building, like that is masonry made of sun-dried bricks or blocks that were that is historical construction, traditional construction in Turkey, and in some earthquakes like 1992, these were heavy damage of these buildings. And nowadays, actually, these buildings survived the earthquake. These are buildings that were exposed to the earthquake in Malatya, and they were not damaged. There was very little damage. So it's a little bit of paradox that we are talking about significant damage of modern buildings, while older buildings, traditional buildings, some of them performed really well. So focus of this presentation, my presentation, is on modern urban buildings, which were most affected. Seismic design codes, implication of design practice. I will skip most of it because of Professor Young has talked in detail on various codes. I would say that out of the three codes that I would single out here on this slide, the one from 1998, the one from 2007, which is more or less similar or the same in terms of implication on reinforced concrete practice, and 2018, which is the latest one. I would say that the most important ones are from 1998 and 2007, because I believe that most of the buildings were built according to those codes, designed and constructed. So I would like to show some details of the construction detailing practice, which are important for this. As Professor Young mentioned, 2018 code is modern code and more advanced, both in terms of analysis and design and detailing. But 1988 and 2007 code are also very good. And in terms of, these are some images showing detailing practices for, let's say, columns on the right-hand side. You can see that, they look similar. We do have some slides which I don't have time to show in comparison with Canadian code, which is the concrete code CSA 823.3 from 2014. Not significant difference. The detailing is good. It's required to provide cross ties, and the columns, as in this case, have to be properly confined, which is critical for integrity and safety in earthquake. So, and there are also closer tie spacing in the columns at the bottom and the top, which is normal practice, with very similar rules related to the spacing as in Canada. And for beams, similar practices are there, with the closer spacing, with the capacity design principles. So in terms of, and I'm showing only the category which is ductile, high ductility, which is expected to be used for these high seismic zones, such as the ones that we visited. So I'm not discussing about lower ductility or more relaxed provisions in that sense. So in any case, for walls, again, good practice was there. These are some detailing requirements for the walls. They had the requirement of boundary elements with a certain reinforcement ratio, which is similar to what we have in the code, in concrete code. But I would say that in Canada, you would find, at least based on what you could see in Turkey, more heavily reinforced boundary elements than what we could see in Turkey, but more or less it's not a big difference. Here is a detail of cross section of the concrete wall, reinforced concrete shear wall with this boundary element, and again there is requirement for some confinement and then cross ties, which are connecting these two curtains or layers of reinforcement, and they're very important for preserving integrity. So again, anchorage requirements are similar to Canadian 135-degree hooks, which we know are required for good earthquake performance. So in any case, with all that said, we have seen extensive destruction in the area. This is a scene from Antakya. It's from my colleagues from the Serbian Association of Earthquake Engineering, who went to the field before and benefited from their experience as well. And causes of damage, these are 5, I would say, causes that I personally would emphasize. One is certainly there was extremely high intensity of shaking at most locations, or many locations at least, which unfortunately we have evidence, and it's been well documented, but we don't have now spectra to show. But for example, Antakya, the city experienced really significant shaking, and it was devastated. So acceleration, just as a reference, one of the stations, and it was very well instrumented earthquake, so there are many of stations that were working during the earthquake, and the records indicate acceleration level of 2G. and it was not a mistake. It was actual acceleration. So, but besides that, there are, and just to say, Antakya, this is the earthquake affected zone. You can see this whole red zone is the fault line, which was more than 300 kilometers long. Antakya, you can see is at the bottom of that fault line. So in this earthquake, it didn't matter where was the epicenter that much. It is the whole proximity or distance from the fault line, which actually for rupture, which matters. So other than this strong shaking, which is no doubt about it, is deficient. There are some deficiencies in the seismic force resisting system. So it's not just detailing, it is seismic force resisting system that they used for these concrete buildings. Then there are some configuration irregularities. There is inadequate detailing of reinforcement in concrete elements, such as shear walls, columns, and beams. And last but not least, substandard quality of materials and construction. So what is interesting, and this is a bit of a difference between Canada and Turkey, and it's subtle, but it's actually important, that in Turkish codes, there are three systems for concrete structures. One is moment frame, which consists of beams and columns and slabs, obviously, and that is one system. Then there is a wall system, which is a shear wall system, which we have in Canada. But then you have a third system, which is dual frame wall system, which is that big gray area in terms of the code definition in Turkey. And in Canada, we don't have that system actually as a lateral load resisting system. So wall system has been clearly defined in Turkey, and it is based on the percentage of the force or the seismic resistance that is being carried by the walls, and that is, let's say in this case, 75% of Turkey. But for the dual system, there is no minimum requirement specified in 2007 and 1998 code, which, as I said, are the same in terms of what is the minimum required amount of walls to be present in order to act as a dual system. And that left lots of space for I would say, interpretation by engineers. And I checked that with the colleagues from Turkey, and that is true. It's a omission in the code. So as a result, there is excessive flexibility of the system in reinforced concrete buildings, and which is mostly due to inadequate amount of shear walls. And I will show you an example that is just one of many examples that we have seen, but just one because of the limited time. It is in the city of Kahramanmaraş, which is a big city, as Professor Young showed it, vibrant city in center of province, Kahramanmaraş as well. And in that city, we visited a complex of 4 buildings. That was our very last visit on the 5th day of our trip, and which on the outside looked very nice. They didn't look very damaged, and indeed they were not too damaged, but still offered lots of opportunity for observation. So this is a typical building. It had 11 floor levels. 4 of them are like a podium type level, and 2 of them are underground. So you can see the upper 2 levels of the podium plus the above portion is like just a tower, let's call it. The buildings were designed in 2016 and constructed in 2019. So we expected it was according to 2007 code, and we had access to construction drawings, which is very useful. So what we can see here from the drawings, this is showing reinforcement plan at one of the floor levels. With the layout of columns and elevator core, which you can see C-shaped elevator core, that most of this is red line, a red arrow shows north direction. So most of the columns were actually aligned in north-south direction. And if you go to the other direction, which is east-west, there are very few of them. There is elevator core, and there are these 6 other columns. So there was, and we found that in other buildings too, that the alignment of the columns was not particularly given a shortage of walls or absence of walls. So what also is interesting that in Turkey, in the buildings that we visited, most of the columns are really oblique, and there is a very gray area between columns and walls. According to Turkish code, again, 2007, it is sufficient for a wall to have a length to thickness ratio of 7 to be called wall. And I believe those are the walls. They were just pushing that limit, not going into for more. So in this building, you can see that, for example, this wall, the length is 175 centimeters, less than 2 meters long. So this is called wall. So, so there are lots of reasons for damage. This was an 11-story flexible building exposed to high shaking. And these are now some photographs of damage to the elevator core, which, as I said, is not too severe, but still you can see some deficiencies. This is a photograph from the ground floor level. And you can see that you can see the reinforcement. This is at the toe of the wall. So there was obviously crushing and the flexural, and then obviously tension compression at the end of this flange web of the elevator core with the longitudinal reinforcement which buckled, because in this wall there were no cross ties. Cross ties were specified, but there were no cross ties. And again, according to information I recently got from colleagues from Turkey who did extensive studies, that was a very common practice in Turkey, lack of cross ties. They were just missing from the drawing. They were not missing from the drawings, they were missing from the constructed site. So I would like to show that also that damage to columns, and another element, or actually the main element, was the column. And if you look at this same building at the upper floors, you can see here circled in red, in yellow, there were damage to the columns. And again, you can see the column and how it looked like. Again, there were no cross ties. They were on the drawing. If you look at the drawing, this was the drawing for that column. None of these ties existed except for the exterior one. So, and if you look carefully, which you probably can't, there is a brick inside the column. So lots of space for improvement in construction practice in concrete construction. So another very important aspect, which was already mentioned before, I would like to say this is the highlight, that there was extensive non-structural damage. Even in buildings that looked actually by careful inspection that had very little structural damage, they had extensive non-structural damage and they had to be vacated, and as we understand, they will be rebuilt. So non-structural damage was extensive. This was observed both in exterior and interior walls. These were masonry infills in these frame structures, and it is obviously can be attributed to significant lateral displacements, drift, which caused this damage, and also to poor quality of these non-structural elements. So this is interior view of some of these infills. They're really completely crushed or fallen out, and at the upper floors, you can see also interior damage to the, again, interior partition walls or infills also completely collapsed. So a strong reason for that is the quality of these materials. These are so-called beams blocks or briquettes in Turkish. They're similar to AAC, autoclaved blocks in North America, but this is the advertisement, how these blocks should look like from the manufacturer. And this is Professor Young showing one of the blocks at the site. We all had to give it a try to see how strong they were. And this is a block after his testing manually. So they really were of extremely poor quality. And according to manufacturers' information, it's 1.7 megapascal strength. So this is how strong Professor Young is, or how bad the masonry is. So few more things. I have just a little bit more to say. Many buildings had irregularities. So whether these irregularities, how much they contributed, certainly yes. Whether they were taken into account in design, we don't know. But common irregularities are weak story, and the other is vertical geometric irregularity, which both of them are in Canadian code, in National Building Code of Canada. Weak story is really a well-known in every earthquake. There's so many weak story or soft story collapses. This earthquake is no exception. And that is the case where we have buildings with open ground floor or even the floor above without these infill walls, and the upper floors are much stiffer because these are frames with infill walls. Therefore, during an earthquake, these bottom floors are very flexible and they have a high demand. There is a P delta effect and they simply collapsed at that level. So we have seen some collapses and this is a photograph before one building in Antakya, and this is after. So these are photographs again taken from, I really like this building because we haven't seen it. It was already demolished by a Serbian association, but we have seen some others not so good cases, but we have seen these type of collapses. Another irregularity is podium, which I mentioned. So this is our building, the one that I mentioned. So it had a podium at 4 levels. And it was irregular, it added irregularity, it was not equal on both sides. So how it was taken into account, we don't know in design. And the third one, very common, which caused lots of non-structural damages, so-called overhangs. That is, in the left-hand side, you can see increase on cross-sectional area, in a plan area of a building after the, I'm done. At the end, at the upper floors, and that was just for financial reasons. And you can see this building, like you can see the red is column line. The blue, the green one shows first level of overhangs, and then the second blue one shows the second level of overhangs. So they were really going over the border with all these overhangs, and these are all non-structural walls without any concrete connecting elements. So very serious problem. This is the same building. So in any case, that is what I wanted to say. Major takeaways Professor Young will show at the end. I would say key messages: many buildings did perform well. Many buildings, reinforced concrete buildings, had a minor structural damage, but severe over the board, across the board, many severe non-structural damage, mostly due to high flexibility of the system. So these are buildings. This is where people from these buildings have ended in containers and in tents. We wish them all the best and fast recovery and to move into their new homes if they cannot. So thank you. I guess questions will come at the end.
Good afternoon. My name is Bishnu Pandey. I am faculty at British Columbia Institute of Technology, BCIT. I'm talking about school buildings. They are a subset of buildings, but they are special because they are meant to keep our children safe. So they are special. So that's why it's a special treatment for schools. I am going to actually present what we saw in Turkey, and then later Allison will tie back with that parallels in Turkey's system of school safety, or what we observed back to BC school safety things. Okay. To start with, we saw good things about Turkey and all that good, but then when it comes to education sector, like other major earthquakes where schools are mostly vulnerable and they are huge impact in education sector, and Turkey earthquake is not an exception again. So what happened here is we saw major destruction, almost 10% out of 20,000 school buildings in whole area, that affected area. Almost 2,000 buildings were damaged beyond repair, so they had to be demolished. And then rest are either minor damage or partially damaged. And out of that, we got that's a kind of performance of school buildings, but what about the real education continuity of school children? And that's where it's hitting really hard. And as of like September, when next term started, school term started, almost 1/3 household did not send their kids to school, and that's attributed to the fact that there are minor damage. Even minor damage is, school children don't want to go there, but of course their own homes are also damaged, and all that complication brings to result of very low attendance in the schools. That's the education impact in the country. I mean, in the region there in the country. And the major observation there, I know I have lots of story to tell, but then just to summarize what the key observation we got in the field is that the school buildings, perform better, in a fair way, particularly when it comes to structural damage. And then the one reason actually what we saw there is not only the configurations or other things, but it's a better workmanship, better control of quality there when it comes to public buildings compared to residential building. But nonetheless, there is severe damage and non-structural damage, which actually put the schools off in many cases, or get the students away from school going there because they are so scared, even if it is just a minor damage. But then other good thing we saw is the buildings which are typically gym buildings, which are separated from main building, they are used as temporary shelter, which are great, communal or societal asset for people there in post-earthquake response. So that is very good thing we saw there. And as I said, again, it is returning rate is very low, and that is what we will discuss later on. But that's a major concern they had. Okay, those are the main observations. But then I want to just go over quickly on the different case studies. 3 or 4 I'm just presenting here, but there are many school buildings we saw. And this is in one of the city hit very hard by the earthquake, and that is on a population of 40,000 people. There 2,500 people died. And almost 90% building damage. In that city, there are, out of 25 schools, there are 10 school buildings are completely damaged and beyond repair. That is very hard hit city there. And we saw 2 school buildings there. First one there, you can see before and after earthquake. And there could be many regions there. We could not go inside, but looking from outside, we see there are dislocation or major cracks in masonry infill. Still, we may see that as a non-structural, but looking there, they don't want to go back there, and that is up to that point, government did not have a kind of decision what to do with that. And from the response spectra, the ground motion response spectra was plotted there against the building code, and we can see there the around the 0.6 second period, that is the kind of approximate period of that building. You can see the ground motion is much higher, and that could be the reason too, right? So there's a high ground motion, as Svetlana mentioned. There could be high ground motion, but also we can see severe damage there. There's another building close by. It is within 500 meter of the station, the ground motion station there. We can see building is okay from outside, but when we go inside and look at there, it's a huge non-structural damage. Again, the partition walls are heavily damaged, and even major walls, their infill walls have a significant cracks. That is what we saw in the post set of school buildings in Nurdagi. This is the second one, Hatay and Hassa, where it's a small village up in the hill, where the ground motion station was right in the building premise itself. And there we see that within 200 meters away, that the upper photograph is the residential building site. It's completely damaged. It's half of the building of that whole village was flattened. But school building there, nothing there. We can see there, except few the tiles in the staircase are dislocated, but that's it. That's it. And you can see that it's just a 2-story building, but they have. I saw at the end there. We could locate some of the lateral load resisting system. There we can see even shear walls. There, even 2-story building, they put shear wall, very robust system, and that's the reason why they have this building intact. Even all the residential building around there are completely flattened. So which is good thing. right? Coming to another building there, not very far from there. So the response inspector, even you can see very similar there from the ground motion for both north-south and east-west. This is a case of kindergarten school where they had a small building there, few classroom there, but they had 280 students before the earthquake. And it did not suffer heavy damage, but what happened is that major damage was the ceiling fell down in the main lobby. And because of that, they cleaned up quickly, but then parents did not want to send their kids to the same school anymore, right? And so it dropped to 80 students maximum. That is what they had, and they are still afraid that, oh, we don't want to send there. And it's again non-structural damage, heavy non-structural damage, no damage in the structure side, but heavy damage in non-structure. Right? And you can see those fall off ceiling, that's bare frame to support the ceiling, and everything is falling down in the main lobby. And that was kindergarten school. And close to that one, here is sorry for that. Here is a technical institute where it suffered heavy damage, even including structural damage. And that's the roof damage there. You can see in left corner up there, and then bottom also. It's beyond just a simple fixing there, right? And it has multiple problems there. I don't want to go more there, but again, when we go to, this is a technical institute, and they have so many labs, laboratories, and workshop, everything, and that's where the most of the damage we see. It's all non-structural damage, but it makes the whole building, not usable, and then they're putting everything away, right? And then even government, it's so many buildings with the labs and all the laboratories, they're all gone. Okay, that is another instant we see. And then this is the last one that I'm showing because it has a characteristic. That one, it did not have damage. It's in Osmania Vache, where we can see the ground motion is a little bit lower than compared to the D1. That is a 2475 earthquake motion at the top. That is what I'm putting there. It's low, but we don't see major damage there. No, very minor damage. That's a good thing, but the story there is this school was assigned to have additional students registered from other schools and other provinces to come to after the school. And at that point, the government assigned, okay, 400 students. And but then how many students came up? It's 280. But by the time we went there, it was only 80 students. Even the point is, even with the minor damage there, they have minor damage, students are afraid to go. And they say, oh, we don't want to go there. So it gives us a kind of sense that, in school buildings, it's not only the structural damage, it's even small psychological impact that they have, students, be it students or parents, they don't want to send their kids there. And that is what is happening there. But another good thing about that school is they have a gym used for temporary shelter. And they put 300 people for 2 months. As a temporary shelter for immediate response, but the problem there, including all others, because of the planning there, is the teachers had to work 24/7. Basically, it's a double duty, right? So that kind of disaster management plan was not there, but it's somehow working there. That is kind of another highlight. So, coming to conclusion, before I give to Allison here, robust design and construction of school buildings pay off. Good, they have a shear wall even in many buildings. Non-structural damage render the school unusable, even if they are okay, but then the students don't want to go, or they are also thinking to demolish in some school. And use of gym block as a temporary shelter, good one, good case study there we see, and even minor damage in school put children out of the school, and provision of cross school admission should be in disaster plan. That is what one of the learning we got. And with that, I like to invite Allison to talk about how to connect that to British Columbia. Thank you.
Thank you very much, Bishnu. I am Allison Chen. I'm a practice advisor at Engineers and Geoscientists BC, and I will be tying our lessons back to from Turkey to BC, because we have a lot of school buildings, we have a lot of vulnerable buildings. And I want to show here, this table showing that in BC, we care equally, or very similarly with Turkey, about the performance of school buildings, both new and existing. So new buildings, we have higher performance levels in the code, and Tony talked about that a little bit. And for existing buildings, both countries have programs for the assessment and seismic retrofit of existing buildings. Here, we have the school seismic retrofit program. So we have the Ministry of Education, back in 2004, they realized that the inventory of existing school building stock was concerning. So they created some money and they engaged Engineers and Geoscientists BC and UBC to create the first seismic retrofit guidelines. Fundamentally, they're for the assessment and retrofit of existing school buildings in BC. They include text-based guidelines and an analyzer, a web-based analyzer, to assess the performance of existing systems and various retrofit strategies to increase the life safety of these buildings. Over the last 20 years, these guidelines have increased to 14 manuals and over 2,000 pages of information. This is all to incorporate new research and state-of-the-art practice and really lessons learned from different earthquakes around the world. So we're going to take the lessons learned from Turkey and update these guidelines. Ultimately, the goal of the seismic retrofit guidelines is to mitigate the risk of seismically deficient buildings in the Ministry of Education's inventory, as I said. So the guidelines, the goal is to achieve a common life safety objective with a consistent approach to the assessment of the resilience. These guidelines enable us to consider different levels of seismic hazard, kind of like the Turkey building code. So it's not just the maximum credible earthquake. There's a lower earthquake as well. Construction type, materials. This is all done using a performance-based methodology, setting drift limits. And it's all done in a cost-effective manner because following the building code is much more stringent than looking at the existing buildings as a performance-based methodology. Looking at the graphic, there are multiple options for performance level. Like Bishnu said, school gyms are often used as shelters following an earthquake, so that is an option for selecting a performance level here. We do have a bunch of lessons to take from Turkey. So these guidelines were written and redeveloped and refined over the last 20 years. But some of the key learnings we got from Turkey were about liquefaction, non-structural components, post-earthquake evaluation, so how quickly that the building assessments happened after the earthquake. There are guidelines for that in BC. We have this as a resource for school buildings particularly, including one here to actually rate the risk of a building based on the structure and the geotechnical conditions. So we have these resources already. We're going to get to use the lessons from Turkey, and we've already been talking about it as a group who develops the guidelines on how to incorporate and just get a little bit better. Before I move on to a few examples, this is the results, the current status of the Ministry of Education School Seismic Mitigation Program. And there is an announcement by the Building and Safety Standards Branch that these guidelines can be used for the assessment and retrofit of all low-rise buildings in BC, which is very, very exciting. So there are other buildings in our province's inventory that could use retrofits. So I'll share just briefly a few examples of some of the systems that we have in BC. These are largely for school low-rise buildings, but also applicable to other buildings as well. Not giving specific case studies, but just some common construction types, issues, and retrofit strategies. So obviously, reinforced concrete frame buildings were very, very popular in Turkey. We have a number of them here as well. So like Svetlana was talking about, a lot of the issues come from the detailing of the columns and the beams. Other issues too are maybe not having sufficient foundations around the walls that exist in the stair core. So upgrade strategies for that would be to add reinforced concrete shear walls around the perimeter or in the interior, increase or upgrade the footings, and maybe add drag struts as well. So that's pretty common requirement. Unreinforced masonry, various different prototypes for this. UBC does a lot of testing to help with the seismic retrofit guidelines. Common challenges with unreinforced masonry are the strength, the in-plane shear strength, out-of-plane connections to the diaphragm. So upgrade suggestions are to add ledgers and increase that connection to the wall, to reinforce, add vertical reinforcement and dowels, and to support the wall out of plane. Often too, the foundations need to be upgraded and drag struts need to be added. More clay brick examples. So really for brick buildings, these are common. Just like masonry, they have the same kind of issues. They can be upgraded with vertical reinforcement and dowels if they are giant brick. If they are just regular clay brick, then one of the common strategies is to just add a reinforced concrete shear wall behind the existing one, brace them out of plane, add new footings, etc., because the existing capacity is really quite low. And then the last couple examples here, wood frame buildings. There aren't a lot in Turkey, but there are a lot in BC for schools, and there are a variety of different construction types just based on the age of the building. So you can see some examples here of diagonal board, horizontal board, walls with gypsum only, walls with plaster only. The biggest issue with wood frame buildings is not enough capacity within the element and connections between them. So that's one of the big upgrade strategies, is to either reinforce what's already there or replace it or increase the fasteners. Often there aren't hold downs or other mechanical connections to resist overturning. So that's another retrofit strategy as well, to increase the hardware, increase the nailing, add a layer of sheathing, and update the footings as necessary. Yeah, so just wrapping it up here, another couple examples. We did a lot of testing over the last 20 years for various types of retrofit upgrade strategies. Really overall, like Svetlana was talking about, and this is not just for school buildings, but lessons from Turkey to hear are that the details really matter. They matter in existing buildings, they matter in new buildings. So making sure that they have positive connections and adequate connections from horizontal to vertical lateral load resisting elements, a clear load path, and all the hardware and overturning resistance are in good shape. Thank you.
My name is Jeffrey Salmon. I'm a structurally IT with Ausenco Engineering. And for the last session before the break, I'm going to be discussing the performance of the healthcare system, or the healthcare facilities. So this is a bit of a reiteration from what Tony had mentioned earlier, but it has a significant impact on the performance of the healthcare facilities. So in 2013, the Turkish Ministry of Health issued a regulation that required base isolation for large hospitals in high seismic zones. In 2017, the seismic design for base isolation was included within the Turkish codes. And so by as of 2017, a total of 72 base isolated structures were located within Turkey. So these structures would have been hospitals, schools, or portions of the airport. Okay. So just to make sure we're all on the same page with what base isolation is, just a quick illustration. So the structure on the left is your conventional fixed base structure. The structure on the right is base isolated. So when this video focuses on the fixed base structure, what we'll see is that maybe the structure is okay, but the components within the building are moving around and falling over. This is one component of non-structural damage. With the base isolated structure, however, all of the deformation occurs at the isolation layer, and then the structure essentially remains intact. So preventing damage to both structural and non-structural components. Okay, so by and large, the types of isolators that were used in the hospitals that we'll be talking about in a few minutes are what's called a friction pendulum isolator. So the photograph on the left is from one of the hospitals that we visited. And then the components that are essentially sandwiched between the concrete components, that isolator that's the friction pendulum isolator, and the two components of it are kind of separated and split open just to show you what's kind of going on there. Okay, so this slide illustrates 12 hospitals that were visited by others that we'll touch on here because it again paints a picture of how base isolation in this case helped the healthcare facilities within Turkey. So on the left, we're looking at a map of the earthquake affected zones. Maybe I can highlight here. So the red lines indicate the faults and the hospitals that were visited, whether they were base isolated or fixed based. Base isolated is denoted by the Bs. So you'll see a B and a number. And then the fixed based hospitals are denoted by an F. So F and a number. Okay, so this figure might take a little bit of explaining, but it does summarize overall how the base isolated structures compared with fixed base structures. So what we have are the demand ratios so this would have been the earthquake demand ratios that the hospitals would have felt. What this means is, so a demand ratio of 1, that corresponds to an earthquake with a return period of about 500 years. A demand ratio of 2, that corresponds to what we use in Canada for seismic design, which is an earthquake with a return period of about 2,500 years. So right away, before even kind of moving ahead, we can see that a lot of the hospitals experience significant shaking. Along the y-axis, so here, what we see is the occupancy status of the hospital. So IO is immediate occupancy. OS is the occupancy is essentially delayed, so they were not occupied, or occupancy suspended. And NA means no access. Okay, so, okay. The second thing that I want to highlight here is that you'll see that 4 of the 5 base isolated hospitals that were visited were immediately occupied after the earthquake. The reason you'll see that one of them, B3, that it had its occupancy suspended. This is because it was reported that the moat around the base isolated hospital had been filled with material, which effectively renders the isolation system doesn't work in that case. So fixed base structures built after 2001, as was mentioned by my colleagues, essentially had no structural damage or very little structural damage, but had significant enough non-structural damages that the hospitals would have been closed. So in this case, I'm talking about these 2 hospitals, F1 and F2. And then there were 2 hospitals, which we'll touch on a little bit later with some pictures, where they were fixed based. They experienced a significant amount of shaking, but they managed to remain operational after the earthquake, which is kind of interesting on its own. Okay, so in these next 2 slides, we're going to compare 2 hospitals that were at the exact same site. So this will be B1 and F1. So just these are highlighted on the left side of the slide, B1 and F1 here. First, we'll talk about B1, which is the base isolated hospital. So again, just to reiterate, B1 was operational after the earthquake. However, there was some damage to the cladding on the side of the structure, which you can see in this photo here. So you'll see some of the cladding had fallen into the seismic gap or within that moat. And there was some cracking that was noticed. Again, this is non-structural cracking in the basement. This did not hinder the performance of the hospital as far as its base isolation characteristics, but it is something to note. So again, at that exact same site, experiencing the exact same shaking, the fixed base sort of, let's say, we're comparing it to its fixed base counterpart. What was observed was a significant amount of non-structural damage, which you can see from ceiling tiles that had fallen. There's a lot of cracking within one of the washrooms for some of the tiles that had fallen onto the floor, and more. Enough that F1 was not operational. Okay, so shifting now to some of the hospitals that we had visited. So first is a fixed base hospital in Nurdahi. This hospital was built in 2003 and then upgraded again in 2015. The photo on the left shows the Google Maps view of 2021. And then a similar shot that was taken in June 5th, 2025. You'll see that there was the one structure, it looks like it would have collapsed. But what we're going to see with this hospital is, again, a significant amount of non-structural damage. The photo on the left, that's showing the cladding on the outside of the building that had fallen. On the right, just a different view with more cladding that had fallen. Looking at some of the interior portions of the hospital. So here, what we're seeing is, this is essentially non-structural damage. The structure appears to be okay, but the non-structural damage caused the hospital to be, to not being used after the earthquake. Okay, so another fixed base hospital. This one did remain operational. This is one of those anomalies that we had seen. This hospital is located, within 100 meters of the fault line. So the photo on the left, that's showing a Google Maps view from 2022. And then June 5th, 2023, you'll see my colleague is standing in, essentially that same parking lot and that is along the fault line. And, there's about a meter drop there. So to highlight, sorry, I realize my cursor is not showing up. So to highlight, that fixed base hospital is located here. And then these red lines are indicating where the fault line is. So the hospital is very close to the fault line. I'm hoping you can kind of see the rupture within the field beside the hospital. This is that hospital, and it was operational. In all honesty, it's not really clear to me why or how it remained operational, but something maybe for further study. Okay, so moving now to a base isolated hospital that was visited in Malatya. So it's a large hospital, it's base isolated. This hospital was operational during and after the earthquake. Sort of an interesting anecdote that was provided by the director of the hospital is that there was a surgery taking place during the earthquake, and the surgery could continue after the earthquake. Really no interruption. And to me, it's sort of an anecdote that highlights the power of base isolation and allowing operational of these facilities after the earthquake. So this should be a video. Maybe. So just to give you a sense, not so much in a cartoon, but I hope you can see the differential movement between the structure above and the fixed portion. So that's the building now riding on those friction pendulum isolators. This is on YouTube. You can find it in your own time as well. Okay, so one other thing with this base isolated hospital is that it had 5 backup generators and additional purifying systems. So if the power were to go out, again, they have redundancy here to ensure that the hospital can function afterward. So these couple photos show the moat around the structure. Kind of interesting here is that what they had put within the moat was what's called like a pumice-like material. Effectively, it's a crushable material. So the structure can move. That reddish stuff that you see in the slides crushes, and the building, the isolation system can function properly. There are other methods to cover the moat. This was one, I guess, that this hospital had used. Okay, I think I have plenty of time. I think this is the last base isolated hospital that I'll be talking about today. So this is in Osmanayi. It's a large hospital. This is one that was under construction when the earthquake occurred. So it wasn't operational before the earthquake, but then it opened shortly after the earthquake. This is a photo of one of the isolators, and then this is me standing beside the other isolator, provide scale. This is something it's kind of interesting. So this is what's called the scratch plate, and it essentially shows you how much a structure has moved relative to the ground. So here, these black steel components, that's rigidly fixed to the structure, and then this steel component is fixed to the ground. So when the building shakes back and forth, this needle scratches on the scratch plate to show you how much the building had moved. So it's just kind of interesting to see, and you can compare that with maybe other methods that you're using to record what's going on in the structure. In this case, I think we saw that it had moved like about an inch. Okay, so this is just showing a few connections. So there are some other detailing requirements that come along with base isolation. Anything that has to cross the isolation plane has to be able to accommodate the relative movement between the ground and the isolated hospital. This is just showing a few of those connections. So this allows the movement, between the fixed portion and the isolated portion. Okay, so just some general observations. The hospitals were subjected to a significant earthquake, as my colleagues have already mentioned. Second, the base isolated hospitals performed well, where they were operational during and after the earthquake, except for the one that I had mentioned where, again, it was reported that the moat had been filled, which effectively just removes the isolation system from doing its job. Okay, and then a significant amount of non-structural damage. I feel like you guys have heard non-structural damage about 100 times today, but a significant amount of non-structural damage to the fixed base hospitals had resulted in them being closed as well. Now we're going to be turning our attention to the preparedness, response, and recovery. This will be covered by myself and two of my colleagues. Okay, let's just jump right into it. Okay, so to illustrate the response and recovery, we're going to look at a timeline over the first few days, and then we'll extend this timeline to look at the first couple of months. Okay, so coming back to February 6th, the first earthquake occurs at just after 4 a.m. local time, and it's early February. So most people are at home, and the average lows in February range between 0 and 5 degrees Celsius. So, try to put yourself in that state. Right after the earthquake, chances are you're calling your loved ones, you're looking around your household for your family members. So, okay, now, as will be discussed in a few minutes by my colleagues, Turkey has a planned response for emergencies such as this one for earthquakes. This is done by the Ministry of Interior Disaster and Emergency Management Presidency. So for short, or the acronym is AFAD. So as a result of the preparedness and response, they have teams on the ground, search and rescue teams on the ground immediately. Now, this search and rescue, in this case, and in most regions, lasted for about 2 weeks. So some of the devices that they had used for the search and rescue, this includes what they called, what was reported as an electronic sound device. So you're trying to listen to people within the rubble to see if you can hear something. Heat tracing systems, again, used within the rubble areas to see if you can pick up patterns of where people might be located. And then they also use dogs. So in some of the reports, the latest time that I had read was survivors were pulled out of the rubble roughly 12 days after the earthquake. So in any case, it's a pretty sad state. Okay, so shifting our focus from the search and rescue, again, that was on the first day. Again, because of the preparedness, they also had food and hygiene products right away. Now, for the first few days, when I say that they had food and hygiene products, this may not be applied sort of around for every area. In some cases, damage to roadways or debris in the roadway would hinder the recovery or the response. You can't get aid to places where you can't travel to. So as access to the affected areas was improved, then food was steadily provided and supplied to those affected areas. I wonder if, nah, that's okay. So now within the first 3 days, the military was brought in for a couple of reasons. Some of these include to provide security and to help set up tents. So everybody that had lost their houses within the earthquake or didn't want to go back into their homes because they weren't sure if it was safe to do so, tents were provided for these citizens. Okay. Now, you can imagine that you have a case where many people have been displaced from their homes, tents are being set up for them, but their houses might still be okay to go into. We talked a lot about structural and non-structural damage. It might actually just be that they have non-structural damage, but they're afraid to go back. So what we see is on February 8th, 2 days after the earthquake, that's when damage assessments were performed by groups of people, either volunteers or people that were part of Turkey, to determine if the buildings were safe to go back into. So, my colleague Şerife is going to talk about this in a little bit more detail in a few minutes. But again, you can think about at a high level, if you can assess the building and people can go back into it, you don't need as many tents. So the two kind of, they kind of go hand in hand. Okay, so with tents, what they would do after a few days, they got a little bit more organized, and tent cities or tent sites were effectively set up or scheduled for construction and then set up again within the first few days. At first, they were tent cities, and then as time progressed, they tried to transition people into container cities. So you can think about a tent. We're going to show a couple of pictures of a tent and a container shortly, but think about a tent being sort of your immediate temporary, and then a container a little bit less temporary. And they were trying to transition people from the tents into these containers. Okay, so now let's look at the rest of the, well, I should be able to go to my next slide here. Looks like we have some technical difficulty. There should be, let's say, March and April shown here. So let's pretend like those are being shown. Within that first month, what they were doing was they would bring in a psychiatric center to help people with mental health. You can imagine that after an earthquake, you're scared to go into buildings. So the mental health support was provided within that first month. Okay. Further, 1 month after the earthquakes had occurred, so we talked about the tents, containers, then 1 month after the earthquake occurred, construction had started on permanent housing, as Tony had mentioned during his introduction slides. Okay. Okay, so on the left, what we're looking at here is something like a container or a tent site. And then in the photo on the bottom is just, let's say, a close-up of one of these tents. The graph on the right illustrates how many tent sites and how many tents were set up with time. So what we can see is by May, there were 3. So the blue line shows you the number of tent sites. So there was about 350 tent sites at that time, with just over 800,000 tents that had been set up. We talked about how people were transitioned from the tents into containers. So in one place that we visited, a gentleman showed us around the container that him and his family were staying in. So on the top, we're looking at that's the full container. And those containers contain 3 rooms. There's a bedroom where you see the bunk beds, and then there's some mattresses on the floor. There's a washroom with a toilet and a shower. And then the gentleman is standing in the kitchen, and there's a small dining area there as well. This would house between 5 and 6 people, and it would be pretty cramped. So that container, it's essentially like a shipping container. It's 21 meters square. This graph just shows the same thing as I had just described for the tents, but now for the containers. I'm going to skip it for time here. Okay, so the small figure illustrates the areas that were affected. And then these images, these illustrate at various stages the container or tent cities that were set up, along with some of the more permanent construction that was ongoing in the different regions. Okay, so this is again very similar, but just in the different regions. Okay, so we talked a little bit about some of the debris that would have been in the roadways. What we had noticed while we were there was the debris that was collected from the damaged buildings. That debris was shipped to sites where it was separated, and so that the material could be recycled. Okay, so some of the reported issues, it sounds like, based on the reading and while we were there, is that Turkey did have a really strong response to the earthquake. But of course, there's always room for improvement. So one was that there was a damaged airport runway, which hindered some of the response and aid in the region of Hatay. So it took 6 days until that earthquake was operational again. Rescue and aid was delayed in some regions due to debris, as I mentioned. And there were also reports of some mismanaged distribution of goods. I think you can understand that after an event like this, communication would be tough. So there were some regions that had reported, let's say, an excess of blankets and some that were in need of blankets. So I think with that, I'm going to turn the slide over to my colleague Şerife to discuss a little bit more about the damage assessments that were performed on the structures after the earthquake.
Thank you. So I'm Şerife Özata from Turkey. I work in Ahiyevran University, and I was a volunteer during the damage assessment process of this earthquake. And now I will mention a little bit about damage categories of the buildings and elements of reinforced concrete structures. Then I will define the damage assessment algorithm and give details about exterior and interior assessment. And what is post-earthquake damage assessment? First, it must be done by a technical team, and it is the process of observationally evaluating and classifying the damage that caused by the earthquake. And it is not the determination of whether the building is earthquake resistant or not, and it doesn't consider the potential damage that a larger earthquake in the region could cause. So when we consider the number of buildings that require inspection and the shortage of the qualified inspectors, the assessment methodology must be rapidly applicable and straightforward. So especially after the 1999 earthquake in Turkey, Professor Dr. Alper İlke and his team developed a methodology. Of course, they made several adjustments and improvements to enhance its applicability. And this methodology can be used in RC and mezzanine structures. Also, it is accepted by the ministry as a general damage assessment method in crisis situations. And you can find details in this reference. So I will start with the building damage categories. There are 6 different categories. And first one is undamaged building. You will not observe any earthquake-induced damage in this kind of buildings. And for the slightly damaged building, structural or vertical elements may have some minor damages. And for moderate damaged building, you will see certain degrees in the capacity and performance of the building. This is an example from the Nurda. And heavily damaged building category, the buildings in this category has significant loss of its pre-earthquake performance and capacity. You see that one floor completely collapsed. And for buildings to be urgently demolished, you will see partial collapse of its one or more floors or noticeable residual displacement in the building. So we give them priority to be demolished since they may possess safety risk to life and properties. And you will see that the building's structural integrity is compromised in this collapsed building. And for the members, we have 5 different damage categories. First one is type 0. You will not observe any crack or compression damage on the structural elements. And for the type E, you need a crack measure, and you will observe residual crack with smaller or equal to 0.5 millimeters. And for type B, you may observe a crack that has width between 0.5 or 3 millimeters, or you may observe a cover crushing of a column, generally, or shear walls. And for type C damage on the members, you will definitely observe a 3 millimeter, you will observe a crack bigger than 3 millimeters, and you will see cover spalling. And for the type D, you may observe buckling of the reinforcement or core crushing or noticeable residual displacement of the reinforcement. So this algorithm consists of 2-stage procedures. We start with exterior assessment. Firstly, you have to check all the facades. So we control all the facades. This is a school. And we have to be sure that these cracks or damages are non-structural. If these buildings may cause any problem or damage to you when you enter the building, so you will not enter and you will not start to interior assessment. But if you are sure about that, these are non-structural damages, then you can continue to interior assessment. And when you go through the building, you will see some cracks or damages. And again, you have to be sure about, are they structural or non-structural damages? So you have to use some hammer or some equipment, some small things, that is this crack belongs to plaster or belongs to column or shear wall. When we check this part, for example, this was not a structural one. So for the exterior assessment, we have 4 different questions. First one is there a total collapse? If your answer is no to this question, then you will understand that there may be a partial collapse or more. So we continue to ask that, is there a partial collapse? If your answer is yes, then building must be urgently demolished. But if your answer is no, then continue to third one. Is there any permanent horizontal residual displacement measured at any story in the building is greater than 1% of the corresponding building? If your answer is yes, then this is heavily damaged building, and but the displacement is bigger than 3%, the building must be urgently demolished. And your answer is no to that question. We ask the fourth one. Does the structure experience a rigid rotation exceeding 2 degrees? If your answer yes, then this is again heavily damaged building. But if the rigid rotation exceeds 4 degrees, then building must be urgently demolished. And your answer to these 4 questions is no, then you can continue to interior assessment. There are different types of interior inspections depending on the urgency of the inspection or size of the building and extent of the damage. These are detailed, rapid, and assessment in crisis situation. When you understand the extent of the damage during the earthquake, so we used assessment in crisis situation. But you must be sure that this is this method is applicable only for low and mid-rise buildings that has smaller or equal to 10 stories, and the building must have equal or less than 800 meter square plan area. And another important thing is we start from the most damaged floor to interior inspection. Again, we ask questions to, I put this damage categories to check which one is this one. Is the number of columns or shear walls, I mean vertical structural elements that have type B damage equal to or bigger than 1? If you have one or more this type of damage on a vertical element, so the building is directly heavily damaged building. You don't need more inspection. But if your answer is no, then ask, are there any type C damaged columns or shear walls in the structure? If the number of them equal or bigger than 2, again, the building is heavily damaged building. But if your answer is no, then continue the third one and ask the question, is the number of damaged element of type B smaller than 3? If your answer is yes to this question, so this building is slightly damaged building. And if your answer is no to this question, then, I mean, the type B damage more than 3 or equal to 3, the building is moderately damaged one. And for the fourth question, are all damages type E regardless of their number? They may be 10, 50, it doesn't matter. If your answer is yes, so this building is slightly damaged one. And if there isn't any earthquake-induced damage, so building is undamaged. Sorry. And to sum up, you see the extent devastation in the Kahramanmaraş city. This is one of the cities of 11. And you see the Turkish printed damage assessment sheet. You may think that during this era, why did you use the printed one? Because we didn't have stable internet access during the first days. I translated it into English for you. We asked some questions and we asked the exterior and interior assessment questions. And after we had an stable access to the internet, we start to use the online forms for assessment. The tablets that we used during the assessment provided by the ministry, and in 1 month, approximately 6.8 million buildings and detached units were assessed. So I totally suggest this methodology to other countries since it's quickly implementable, easy to follow and understand. Now I've finished my part, so the floor is yours, Allison. Thanks for your listening.
Okay, so I'm going to talk a little bit about the ongoing recovery efforts and the things that we saw in the 3 and 4 months, or at the 4-month mark when we were in Turkey following the earthquake. And then from there, I'll bring it back up to big picture and talk about emergency preparedness in general. So when you think about response and recovery, we usually think, never mind. We usually think about the first few days and weeks, thinking about the search and rescue, providing food and shelter and post-disaster building assessments. But there's so much more to recovery than that. So municipalities and NGOs and governments are tasked with offering a variety of services for a prolonged period of time through the recovery process. So some examples are providing meals in an ongoing way. The bottom right here, I'm showing a tent that was in Kahramanmaraş in 4 months later. So there's still a need for people to get meals. Public transportation was provided for free in the same city for 4 months. That was ending the week that we were there. And psychological support is really, really important. So students would get that when they got to go back to school and talk with their counselors, but that wasn't available to adults. So we visited a purpose-built community center. There's a kitchen, there are phones, internet, games, books, even books on earthquakes for people to learn, and really just a place to socialize and bring that network back together. On the development front, of course, development is still ongoing, and that looks different in different places. You can see in the top left corner, there's a prefabricated steel building. So that's really common for single family homes, little neighborhoods like that. And for taller multifamily buildings, tunnel form construction was used, or is the preferred method. And that's kind of a prefabricated system that you actually do on site. So the walls and slabs are all cast at the same time. Home life, long-term recovery is really long-term. And that's something I didn't really notice until I didn't realize, maybe knew on some level, but didn't until I went to Turkey. And so those prefabricated homes that I was just talking about, that community of 400 homes is expected to be completed in January 2024. That's a 9-month construction process to get 400 homes completed, and that's 11 months after the earthquake. And other than the people that actually get to return to their slightly damaged buildings, slightly damaged homes, I would say that 9-11 months is probably pretty best case scenario. So while everyone else is waiting, they're, like Jeff talked about, they're in tents and they're in container cities. And as more and more containers get delivered to all the different container sites, more people are moving from tents into containers. School life. So a lot of schools were closed for about 2 weeks to accommodate the post-disaster building assessments. But the goal was to get the kids back to school as quickly as possible. So whether that was in the building that was assessed to be lightly damaged, or in tents, or in prefabricated schools, obviously that didn't happen in 2 weeks, but that's a little bit later, or temporary structures, then that got to happen. As I said, some school gyms were used as shelters as best as possible, but the schools actually got to function in the two purposes. So they'd be used as schools in the day and shelters at night, just to house as much of the community as possible. And we even found that in the functional schools that we visited, most had at least one teacher and their family living in the school as well. Just out of necessity and to be there for the kids. But schools are really a safe place for kids and communities, so it's really important that they perform well so that they have that consistency and that normalcy. So yeah, Bishnu said too, some people were afraid of schools, so whether the schools couldn't be used or whether it was personal preference, some did actually continue in tents. And work life, just like the homes, want to get back to business as usual as best as possible. So businesses are moving back into their lightly damaged buildings, cordoning off areas that are not usable at this point in time, and moving into prefabricated structures and containers, and that's on a lottery-based system. So moving into earthquake preparedness. In Turkey, they really are well prepared for the earthquake. They've seen them regularly. They know how to respond and react, and that's really important. There's one key takeaway is just how important it is to be prepared, to have your networks in place and be able to mobilize immediately, because that's how they were able to get that response and recovery process going right away. There, of course, were areas for improvement. There always are. Tony will talk about that at the very end. And I've just got a graph here. The emergency preparedness is mitigation, preparedness, response, and recovery. You can see the relative timeline for each of the stages. There are many organizations involved in emergency preparedness in Turkey, but these are the two key players. AFAD, which is the Disaster and Emergency Management Agency, they're responsible for the Disaster Risk Reduction Plan and the Disaster Response Plan. And their key responsibility is to actually execute the disaster response process. The Ministry of Environment, Urbanization, and Climate Change is the other key player there. And they're responsible for activities related to spatial planning, geological surveys, damage assessments, demolition of damaged buildings, and debris removal. So you can see how they really work well together in the response process. They have a lot of other responsibilities as well in terms of improvement of professional services, regeneration and building inspections, climate change, and more. not going to spend too much time on this, but the Turkey Disaster Risk Reduction Plan. So other than updating the code every time we can learn from the earthquake, there are other things that the provincial, national, and local governments can do to minimize risk. So just like we do in BC, Turkey follows the Sendai framework, which has 4 properties: understanding the disaster risk, strengthening disaster risk, investing in disaster risk reduction and resilience, and enhancing disaster preparedness for effective response. And this is developed with a variety of industry partners who have experience in responding to earthquakes. As it relates to earthquakes, the Turkey Disaster Risk Reduction Plan includes 7 objectives and 29 actions, including understand the crustal structure and model, monitoring crustal deformations and fault zones, and preparing liquefaction potential maps, and local scale soil amplification potential maps, which we can relate to here in BC with the Metro Vancouver Seismic Microzonation Mapping Project that will be coming out next spring. The disaster response plan, so AFAD is responsible for this as well. They're responsible for coordinating the response after they develop the plan and when it happens. The disaster response plan is multi-hazard. It's designed to minimize operational risks during disasters through an integrated planning approach. The key is really to identify all parties responsible and what their main role is to gain experience from previous disasters, update the plan, update the process, and do better the next time. As you might imagine, the key things for success in any disaster response plan are for everyone involved to know what their responsibilities are, to own the plan, to really feel like they're involved with it, and it's important that they do their job, that they communicate with each other, and that all actions are done on time and in accordance with the plan. So just a couple examples of how Turkey mitigated, prepared, responded, and recovered to this disaster. So they update the codes. We've talked about that a lot today. They have particular requirements for schools and hospitals and programs for retrofit of buildings. Preparedness, they have the disaster response plan. They have the risk reduction plan. They do earthquake drills for students. And then in terms of response and recovery, I've talked about this a lot already, but they were already ready to go with their search and rescue and post-disaster building assessments and providing supplies, and they had everyone there. And the recovery process is ongoing. When we were there 4 months ago, the reports in Antakya and Hatay for the moderately damaged building or the lightly damaged buildings, it was coming back to decide which buildings would be retrofitted and which ones would be demolished. So that process is ongoing. That's in the recovery phase, and rebuild is starting and it's continuing. So some buildings are going to be reconstructed in place, which means that they need to be demolished and the debris removed before they can start. And others are going to be relocated, either because of those logistical challenges or because they want to avoid some of the more challenging geological considerations like liquefaction and avoid those high amplification areas.
Thank you very much for joining us in this seminar, and special thanks to the speakers for their great lectures. We received so many good questions from the both online and in-person audiences. It's very hard to collect some of them to be covered, but we try to cover most of them as much as possible here. Keshab, I tried to start with you with some questions regarding the liquefactions and ground amplifications, actually geotech questions.
Sure.
Is that how to design for liquefaction in the project? They're asking about any possible collaboration between the structural and geotech engineers, methods. What does it mean exactly? What's your experience in that? Let's start with the liquefaction. How to design for liquefaction in a specific project?
So, like for liquefaction, basically we have two ways. Either we can improve the ground conditions. There are several methods to improve the ground conditions, like soil compactions, densifications, and like modifications of the soil properties, providing additional drainage, reinforcement of the soil. That's the one way. And second way is we can design foundations or structures that can sustain the movement due to liquefactions, that can sustain the like inertial loading with kinematic loading due to liquefaction. So there are several ways we can apply mitigations, or we can prevent the structures collapsing due to liquefactions. So either ground improvement, or we can design the structure accordingly. But generally this is very site specific. I can't say right now, okay, we can do step 1, step 2, step 3. It's based on we should do the liquefaction triggering analysis. We should estimate the consequences of liquefaction. There are several steps.
Another.
And then even like if you see the response spectra, you can see the soil classifications. Generally, like in context of Canada, like soil type F, it might be the equal to the liquefiable soil. So even within the soil types, there is different response spectra. Yeah.
See. Thank you. What about the ground amplification? Did you find any evidence of ground amplification in Turkey's earthquake?
I didn't notice, or I didn't observe when because I didn't notice when I was in Turkey, but I've gone through several reports. They reported that significant ground applications in many cities, or in many locations throughout the region.
Okay.
Yeah.
Thank you. Let's switch to the codes. The presentation shows that Turkey building code is very good and consider the seismic loads carefully. So why there were a lot of collapses and damages, Tony? Could you please briefly explain it to us?
Sure. There are many reasons for these collapse we are seeing. One, this shaking was a bit beyond the seismic shaking we designed it for. So in all level, in the horizontal and vertical directions. The other thing that we have to think of is this is back-to-back earthquake shaking, which we never seen it before. The building code did not observe two magnitude 7 earthquake hitting one after the other. We did see some of the construction poor quality, which some of the requirement, but the one I'm showing is the latest code. And of course, this construction was done on the older codes. So some of these advanced application for the building code was not fully implemented in the building which was collapsed.
Okay. Is there any requirements in the code for saving the occupants? It means, does it design based on life safety or damage prevention? This is actually another question coming from the audiences.
Okay, so I've been studying the Turkish building code for weeks now, and thanks for Professor Alemdar's support, translating it for me. The most recent building code in Turkey, the 2018 building codes, provide multiple level performance objective at different level of shaking. But that particular code was once again not implemented for those buildings we see in the disaster zone. So I expected if they follow the building code properly for the brand new ones, which is built after the 2018 code, they will have very good performance.
Yeah, thank you. The next question I picked is regarding the level of damage. Svetlana, maybe you can respond to this question. why buildings which looks similar with a similar shape and located in the same area, one is collapsed and the other one is just slightly damaged?
That is a difficult question because you need to have more information about, first of all, not only about the construction drawings, as we indicated, I showed in the presentation, because drawings may be fine, but maybe one of the buildings was constructed properly according to the design and the others was not. And again, the fact that in Turkey there was this concession or some opportunity for building owners, developers to get permits, even though buildings were not done according to the code. It could be one of very strong reasons, because once the building is constructed and without further information, it is impossible to say whether those buildings that collapsed were indeed. So I'm sure the evidence is there, but we did not have access to the information. So it is either a glitch in construction, maybe in design too, or it is that just the buildings that look similar architecturally were essentially very different when it comes to structural details and, or as I said, even deficiencies in the system when you look more carefully. But it would take more serious investigation than just saying it.
Can we relate it to something like the local effect of soil?
Well, it could be also effect of soil. So there are several possible reasons, but it's very difficult to tell. We actually visited some of the buildings. I didn't show because there's so much information for all these 5 days. For example, in Kahramanmaraş, where were 2 identical buildings on the podium, and one of them collapsed, and the others is standing with some damage. But and there are several examples of that. So they were done by the same developer as part of the same project, and one collapsed and the other didn't. So it could be the effect of soil, but if the buildings are so close, it's hard to believe that. So one of them could have been done with a higher standard of care in construction, and the other not. And I think it would require forensic investigation to find that out. But once there is no strict control in implementation, it's very difficult to tell what are the reasons.
Bishnu, do you have any comments?
Yeah, I can add on that one. Definitely, we don't know that much of detail what happened. But then one on top of what Svetlana mentioned, one possibility, another possibility is that when there are 2 identical buildings sitting one to another, that's if the buildings were designed without much of global ductility, let's say, to perform very well until the elastic range is there, and if there is not ductility, system ductility present there, and then with a small changes in construction, that one may trigger into complete collapse, another would be just an elastic zone. So, without having ductility. So that situation may happen there, that in other earthquakes, we have seen that one. If system was not built, getting a crack and then still getting well under the under the earthquake shaking, then we can see the difference. But if there are not available ductility there, it will just collapse without seeing it. But then just a little bit less than that would look like a completely elastic zone, so we can see perfect one. So that situation may happen in other earthquakes. That is what we observe. But this one, we have to look that way, whether actually that happened here. But just I'm just telling you a possibility there.
Okay, thank you. We also ask for non-structural damage to the buildings, and I want to incorporate what we learned in a Turkey earthquake in BC in case of any earthquake happens in future here. What do you think? Is it similar scenarios for BC buildings?
Okay. Yes. Yeah, I can take that one. We have actually in our code provisions for non-structural mitigation, or how to fix the non-structural items, and then there are all the provisions to design for that one. But at the same time, are we applying that one as a strict like a rules and regulation we do for structural? May not be. And that's where the one problem could be. But as Svetlana earlier in the earlier part, she mentioned that when we talk about non-structural, it has different components, like some are just equipment, some are functional components, some are part of the structure, but they are not under the structural load path. So for the part of the structure which are not under the load path system, that are really vulnerable there. We see with the brick and blocks that Svetlana mentioned there, that part we may be better off on that. But how about other functional things and other like cosmetics or equipments, fixing those one? We have to work on that one. I would not say in the negative side, but we have to work on that one, because that's really the non-structural things are really costing a lot, and also many times could be killer, and that may put our schools or hospitals or important buildings unusable. So that's where we cannot immediately back into foot after the earthquake. So that's where we have to work on that.
Okay, thank you.
Yeah.
Yeah, please.
Yeah, I would just like to add, it's not only the damage, it's really a high risk of injuries from non-structural components. When we think of buildings, we think, oh, this column or beam is going to collapse, but it is any partition wall can cause, or ceiling can cause very serious injuries to inhabitants, or non-structural, let's say veneers falling out, they can cause. So it's a threat to the human life. So at the end of the day, if one's family members die in an earthquake, it doesn't matter whether it's due to structural or non-structural, and that's what is happening in Turkey. They really don't care. Some of the inhabitants of these buildings that we visited, we were trying to convince them that these buildings are safe, because they were asking those questions of us. And structurally, they were not damaged, but they simply would never go back to that building if their family members, children, or any members that they died there, or even neighbors' children died. So it's a very serious issue, and I don't know what kind of counseling would be needed to convince them that those buildings are good to go if they replace those elements, non-structural elements that have been damaged or collapsed.
Okay, thank you. Allison, there is a direct question regarding the SRG. We are asked, when will the lessons learned from Turkey earthquake will be incorporated in the SRG, or modified to how we can incorporate it?
Sorry,
how we can implement the lessons learned from the Turkey earthquake into the SRG?
Yeah, so the next seismic retrofit guidelines, we actually just finished a contract on that for SRG 2023. That's with the ministry right now, and that will be published in the coming months, and then there will be new training. The seismic retrofit guidelines 2020, there is training available on that online, so you can do that already. And so we're working on the next version. Some of the top 4 things we'll look at, again, liquefaction, increasing, looking again at the details for that, some good retrofit strategies so we can incorporate those into school seismic retrofits, looking again at those, what we call operational functional components, but non-structural components, making sure they're all restrained. So HVAC systems, ceilings, bookshelves, anything like that. The post-disaster building assessments, again, we can improve those just to speed up the recovery process a little bit. So it takes resources away if you can already estimate what the damage is to your building based on the design level of performance and the design level of shaking versus the measured shaking. So those are some of the key things that we'll work on right away.
Okay, thank you. Now let's switch to base isolation, Jeff, or maybe Tony, you can help us to respond to these questions. Did we get any idea of the cost impact of base isolators compared to the capital cost of the building? Did we get any information out of that?
No, I don't have any info on the cost increase compared to the fixed base costs for those same structures.
Yeah, it's particularly asked about the Turkish base isolators. What about you, Tony? What do you comment on it?
Right now, the base isolation technology in Canada, it's slightly higher than fixed based in two ways. One is that we don't have that many projects. So right now, the center block is one of the distinct projects where require quite a bit of review and re-review of those things. But overall costs for those construction, base isolation are not more expensive. When the volume is up, we can probably make it cost neutral or even cheaper. You may ask me, how can it be possible? How can you have a higher performance building but cheaper? That's because if you do with the fixed base structures and to ensure you have high performance as good as, for example, almost damage-free or lightly damaged after earthquake, they'll require us to put in a lot of reinforcement and ties to it, just to make sure almost an elastic design. But when you started putting a base isolation, your demand to the superstructure and your foundation are drastically reduced. And that's where we save those money and started putting on mechanically developed devices, which can achieve the job. Base isolation, just one of the technology, which is very mature. We have tested it and we use them in many projects and proved through this earthquake it works. Dampers is another one. One thing about base isolation, the cost right now, the device is not that onerous, it's not that expensive. We put some extra money for peer review of those projects, but as soon as these become more prevalent, I think those costs will reduce as well.
Okay. Yeah. Okay. And is any hospital in Metro Vancouver's retrofitted by base isolation or constructed by this technique?
Not yet. Hopefully soon. This is clearly a proven technology in Turkey, in Asia, Japan. Many of the buildings are base isolated, even single family homes. And it could be as low as $30,000 to isolate a single family home. It's nothing compared to the cost of the building.
Yeah, I believe, and the information that we got in Turkey and these hospitals is that they're very proud that base isolation devices and all the practically other components were made in Turkey. So they're all available as a local by local manufacturers. So that makes also the cost lower than if it is imported. So they really probably it is the mechanism that since the law was issued in 2013, I'm not sure when this manufacturer started, but at this point it's all local and it is very important. I've seen, I'm not sure how reliable it is, but it is by the manufacturers, the information that one device costs about 4,000 euros. I think it's maybe 6,000 Canadian dollars. They're very big, as you could see from Jeff's presentation, and they're like hundreds. There is information in the report that he mentioned about the number of isolators, I believe, and it's available. So it's a large number, but since they're mandatory, they were not comparing it with the cost of non-isolated building, if that is mandatory. So they're very proud that they have their technology and they're able to implement it in Turkey. It's important to mention.
Svetlana, is it possible to use this technology for taller buildings?
I believe Tony may be the better to say he was doing some solutions for taller buildings.
The reason we are asking is that for allowance displacement at top stories.
My answer to almost everything is possible. Yeah. I know we're pretty short on time, but technology-wise, it's possible. It's not as effective. The base isolation provide very effective reduction of the earthquake load. One of them is that it isolated the forces, so the forces transmitted to the superstructure foundation are drastically reduced. But the other significant impact of the base isolation is that elongated the period of the structure. In Canada, we put into the building code that if you need to isolate the building, the isolation period need to be elongated by 3 times of the fixed base. So if I have a high-rise building, which is already very long period, then the requirement for me to make the isolation will be 3 times of very long period. It's just a little bit more tricky to apply. The Japanese have started applying this to high-rise building, and what they do is that instead of doing base isolation, they do mid-tier story isolation. So a high-rise building will be cut into many layers, and then each will be isolating by itself. Theory and validation from experiment shows it works, and some of the real projects in Japan are already doing mid-tier isolation.
Okay, thank you. I'm trying to generalize some of the questions to get the most benefit out of it. Svetlana, maybe you can explain how was the similarity of our buildings in BC vulnerability to those what we observed in Turkey earthquake?
Well, that is a good question, and journalists and I think people, common people ask that, wonder about that, and engineers too. Certainly all the reinforced concrete buildings in BC are vulnerable because if they were done before the modern codes, so let's say 1970s, 1960s, before that time. So there are existing buildings in BC, in Canada that are vulnerable. But what makes them, I would say, less vulnerable than those in Turkey is that the quality of construction in general was better, and quality of construction is an important issue. But as far as the behavior and what Bishnu mentioned earlier, since they did not have the ability for, let's say, modern principles of capacity design, so that they perform in ductile manner after if the earthquake is beyond the level that they were designed for, that is still the fact, and that is the vulnerability which can be removed for really severe earthquakes that may be expected here just by retrofitting. There is no other way of removing this vulnerability. But quality of construction, at least what I worked in practice, what I've seen cannot be compared to some of the buildings that we've seen in Turkey that have been exposed after the earthquake.
Okay, thank you. Let's go back to schools. Bishnu. What lessons from the performance of school buildings in Turkey we can incorporate to our buildings in school buildings in BC?
Yes, there are many, but to pick one or two, that one building I showed in my presentation, it's just a 2-story building, simple community building, elementary school building, but it has a shear wall and it has a redundant lateral resisting system. That shows the emphasis that they give to school, and that is what we can do here. And actually, we already started doing that one because we are putting lots of emphasis on schools, and being there not only in the really high-ranking or high-risk ranking schools, but other schools too. So the idea is to make schools high importance and to make them even going to a post-disaster performance that is making gyms and others even more robust. That is what we can do, and we are doing it. So that is what the lessons from there. But then at the same time, now we saw in Turkey, there are many, again, coming back to non-structural items there, they may not, or they simply overlooked on that one. And that's what happened. But what really is important that in our observation is even small damages or some minor kind of tile fallings or ceiling falling there. And that makes, students, as I again repeating that one, students, parents, everybody scared of. So the education is not continued there because of that. So we have to learn that lesson. It's not just a life safety. We may go beyond life safety to make it really good system, good robust system for schools here. That is what I would say.
Okay, thank you. And Jeff, regarding the hospitals and healthcare facilities, what can BC learn from the earthquake in Turkey and their damage scenarios about what we observed over there, what we can learn from them, and how we can incorporate it in our buildings in BC, hospital buildings also.
Yeah. Okay, so this one might be maybe a little bit obvious after all the discussion about base isolation, but I mean, I think what we had seen in Turkey is that the base isolated hospitals performed very well. Just coming back to this anecdote about how, surgery was ongoing during an earthquake and, the surgery was effectively uninterrupted. So, I mean, if BC wanted to incorporate something like a base isolating critical infrastructure, that would be, immensely helpful. That's what we observed in the Turkey earthquake.
Okay, any other comments from Svetlana, Tony?
Yeah, I agree. That is the way to go, and no doubt about it. I would say that when we talk about base isolation, it's certainly more complex from the, I would say, implementation point of view to implement it in existing hospital buildings than in new buildings. So I would say this Turkish law, which is very good. Okay, we had this practice which we of conventional construction, and at one point we stop it and we move on with the modern technologies. That's certainly a way to go. It is also possible to do, of course, with existing buildings. As we know now, Canadian Parliament buildings are being isolated, which are, very ancient, very old buildings, and it can be done, but it is more complex and more expensive. But certainly some form of legislation that could be implemented in BC and possibly other parts of Canada would be very useful for future construction, which are going on all the time.
So, just to add to the point of base isolation for existing structures, it's my understanding that the first base isolated structure in Canada was a retrofit of the school in BC. So, maybe it is. I don't want to say more expensive, but it's possible. It's been done.
My duty for the next 5-6 minutes is to wrap up the seminar for the day. And thank you all to stay with us until this hour. I prepared a very quick slides. I have to do impossible speed, but I will do it quickly. First of all, I would like to once again to thank all the people who make it possible, either in person here, our IT team. We thank them very much for making sure everything is running smoothly. We also like to thank our media teams, fully announces the event to people in our school, in our city, in our country, and around the world. Today, we have over 800 people registered for the program from 24 countries and every provinces in Canada. So we are glad this information is out there, and we're very grateful for all of you attending this. The financial support is provided by UBC Applied Science, and we're thankful for UBC Applied Science. From SEABC, the certificate program, thank for John for raising the hand, saying that they were backing us up to make sure the knowledge we gain from this trip are all given to our colleagues here in BC and around the world. And we also want to thank Canadian Association of Earthquake Engineering for providing the financial support for some of our members to attend this particular excursion, and also the firms, that engineering firms providing engineers to join us for this trip. And of course, this would not be possible without the local context, all these peoples, and we have met and become new friends in Turkey. Once again, my team consists of myself, Professor Carlos Ventura, who is listening online, Professor Alemdar, Professor Svetlana Brzev, and Dr. Mehrtash Motamedi from UBC. And we also have Dr. Bishnu Pandey from BCIT, Allison Chen from EGBC, Jeffrey Salmon from Ausenco Engineer, Canada, Keshab from BGC Engineering, Şerife from AEU in Turkey, Oma from SUR from Rome, and then Vilhiko from University of Belgrade. Well, in June of this year, we decided to send a Canadian team to actually check it out, this big earthquake event. And we decided and we started planning, and it's a very lengthy trip. But over the course of 5 days, we have been working really hard. Our team showed up and all met at the city of Gaziantep from all different locations, all different routes. Within these 5 days, we've been working hard. We were on the bus more than 50 hours. So every day, more than 10 hours on the bus, and then we go out and examine of the site. We travel to all major earthquake sites. We're very fortunate to really observe firsthand experience about the damage during this earthquake, and give us a perspective how strong Mother Nature is and how strong the damage happened to all these infrastructures. We work closely within our team and with our local engineers who is working with us along this trip in examining structural system, and we deliver our Canadian knowledge with them and figure out how to examine structural systems. Also, the foundation failures, we were observing and we're going around and checking out with them. We have observed the reconstruction sites where they very kindly showing us how the entire village or an entire town are actually reconstructed. And they have fast, rapid technology, cost-effective technology to start getting those built. We visited them, private dams, where we have invitation to go in, talk to the engineers, management system, understand failure and how recovery should be done on those areas. We brought in our toys from Canada, and we started observing and doing measurements ourselves. We visited the hospital, and you have seen in many, and we are warmly greeted by real medical doctors, who the president of the hospital greeted us as guests of honor from Canada. And we walked through and examined the base isolated building with them. In fact, I spent the whole afternoon going through the basement with them, checking the structural safety. And we provided our engineering guidance to ensure those buildings will perform well after the next earthquake. We were warmly welcomed by the local government. We met with many government officials in every town, every city. We were greeted by the head of the disaster management, the mayors, town mayors, or village head. We were even invited to talk to many mayors to talk about how they handle such emergency and how we can learn and work with them to ensure such disaster happen in our part of town, we can handle it. We're in Kahramanmaraş. We were invited to the city hall and meeting with the member of the parliament and discuss our presence. We were heavily followed by Turkish local news. So we were like celebrities. We were going around, news was following us. And we are all over the Turkish news of the Canadian teams are in town. Along the way, we did the Canadian ways. We mingle well with our locals. We have made many good friends, which will last for a lifetime of experience. And of course, through these trips, I'm very honored to take my team. We bonded for five days, day and night. We wake up at 6 a.m. By 6:30, they better show up in the lobby. We have breakfast and we go. By the time we came back, it's usually 11 p.m., sometime past the midnight. But over this time, we started to become a very strong and bonding team. Then these are my academic family now. We had a great time walking along, learning from each other. And today, we were lucky enough, through the support from our financial organization, we come here to present what we have learned. A report will be prepared, and today is the first series of the things we presented. We were lucky enough today by the Consul General from Turkey to give the opening remark, and we went through today's seminar. All the things are recorded, so sooner or later you will find our applied science team will be able to show you where the recordings are. Here are some of the takeaways. This is truly one of the biggest earthquakes experienced by mankind. 11 major city centers has been completely destructed by this earthquake. More than 14 million people were affected. That's half of the population, close of the whole Canada. Very sad, over 50,000 people have died in Turkey, and over 100,000 people were seriously injured. We see many buildings were damaged, and total financial loss to Turkey at the moment already tallied to be $103 billion financial losses. Some takeaway from the geotech and seismology side. This is truly a big earthquake event. In every direction, vertically, horizontal, in every direction, the ground motion was significant. We see failure in the foundation, we see liquefactions. I am here to present it to you. I think Turkey is one of the countries focused heavily in earthquake codes. I'm very pleased to see the latest earthquake codes they are putting up together resemble what we're doing here in North America. And I'm confident that they are able to continue to do well if they are fully implemented. I'm particularly proud of our Turkish colleagues. They are not afraid of using novel technology such as space isolation. And they prove to be working. Over 70 major infrastructure in Turkey started using base isolation, and they are protected after this earthquake. The performance of the residential building, generally, if they're older, built by older codes, we know they are very vulnerable. But if they build by newer code, follow the code properly, we see very few collapse. So they did very well. We see many non-structural damage. So there's something Canadian needed to start pay attention to. And into the school, our colleagues in Turkey do very well. So the schools are ready to be sheltered for past earthquake. Okay, and the health facilities are doing very well. And we hope this kind of mentality will bring here to Canada. And our Turkish friends are doing very well in preparing what they do. And we must learn from this community. And so make sure the next earthquake hits our region will be safe and sound. With that, I conclude the seminar for today. And thank you for with us for the whole day. Thank you.